Voyager 1 is going to die. Not soon, but eventually. The signal will go silent, the power will cut out, and the most distant object humanity has ever built will become a ghost, drifting through the dark. What is the last place it actually reaches before that happens? The answer takes you across billions of years, past dying stars, and to the very edge of what physics can describe. If you are someone who genuinely loves having your mind blown by the cosmos, make sure to subscribe to the channel. Now let's get started. To understand where Voyager 1 is going, you first need to understand what it has already survived. Because the path this spacecraft has taken is nothing short of miraculous. In its early years, Voyager 1 flew past Jupiter in March of 1979. What it sent back absolutely shattered what scientists thought they knew. The images showed a planet alive with chaos, storms the size of entire continents, a ring system nobody expected to find, and most jaw-dropping of all, a moon called Io that was actively erupting with volcanoes. Not dead rock, not ancient craters, living, breathing volcanic fire in the outer solar system. That single discovery rewrote the textbooks overnight. Then, in November of 1980, Voyager 1 reached Saturn. It gave humanity its first close-up look at that iconic ring system, revealing it to be far more complex than telescopes from Earth had ever shown. Thousands of individual ringlets, gaps, waves, and braided structures that physicists are still trying to fully explain today. It also flew close to Titan, Saturn's largest moon, and discovered it had a thick orange atmosphere. An atmosphere on a moon. That was something nobody had fully anticipated. After Saturn, Voyager 1 used the planet's gravity like a slingshot, a technique called a gravitational assist, to hurl itself up and out of the plane of the solar system entirely. That single maneuver set the course for everything that came after. It meant Voyager 1 would never visit another planet. But it also meant it was heading somewhere far more significant, toward the edge of the sun's influence itself, and beyond. For decades, it just kept going, quietly, faithfully, transmitting data back to Earth across an ever-growing distance. And the signal, traveling at the speed of light, took longer and longer to arrive. By the time Voyager 1 had been flying for 35 years, its signal took over 17 hours to reach us. Think about that. You send a message, and you wait 17 hours just to know it arrived. Then, in 2012, something remarkable happened. Scientists analyzing data from Voyager 1 noticed a sudden and dramatic change in the particles surrounding the spacecraft. The stream of charged particles blowing outward from the sun, what we call the solar wind, had dropped to nearly zero, and in its place, Voyager 1 was now bathed in a completely different kind of particle, one that came from outside our solar system entirely, cosmic rays from other stars, from distant supernovae, from sources scattered across the galaxy. Voyager 1 had crossed the heliopause, the boundary where the sun's influence ends and true interstellar space begins. It became the first human-made object in history to leave the solar system and enter the space between the stars. On August 25, 2012, to be precise, Voyager 1 officially entered interstellar space. And here is where things get truly mind-bending. As of 2024, Voyager 1 is more than 23 billion kilometers from the Sun. 23 billion. If you tried to drive there in a car at 100 kilometers per hour, it would take you over 26 million years. It is traveling at roughly 17 kilometers per second, which sounds fast, and it is by human standards, but on a cosmic scale, it is barely a whisper of movement. The Milky Way galaxy is 100,000 light-years across. Voyager 1, at its current speed, would take about 73,000 years just to travel a single light-year. So in terms of galactic distances, Voyager 1 has gone essentially nowhere. It is a speck, a grain of sand that has tumbled off a beach and is now floating in the ocean, thinking it has seen the world. But here is the thing, that is not the point. The point was never about how far it goes. The point is that it went at all. Now you might be wondering, what exactly is out there between our solar system and the nearest stars? What will Voyager 1 drift through in the thousands and millions and billions of years ahead? And what does the universe even look like from that far out? That is exactly what we are going to explore, step by step, starting with the region it is crossing right now, interstellar space, which is far stranger and more violent than most people imagine. If the idea of deep space being unsettling is something that already gets under your skin, and honestly, it should, check the video on the card above exploring why deep space gets more terrifying the further you go. It pairs perfectly with what we are talking about today. It dives into why the further from Earth you travel, the more the universe stops feeling like a place and starts feeling like something else entirely. The link is in the description and pinned on the comments now. Interstellar space. Let us talk about what it actually is. Most people imagine space as a perfect vacuum, completely empty, totally silent, absolutely nothing between the stars. And while interstellar space is certainly emptier than anything you could create in a laboratory on Earth, it is not nothing, not even close. The region Voyager 1 is currently passing through is called the local interstellar medium. It is a thin soup of particles, mostly hydrogen and helium atoms, left over from ancient stellar explosions, slow stellar winds, and the general turbulence of a galaxy that has been exploding, collapsing, and reforming for over 13 billion years. The density is almost incomprehensibly low, roughly 1 atom per cubic centimeter in some regions, compared to the trillions of atoms per cubic centimeter you have in the air around you right now. But those particles are there, and they interact with Voyager 1 in ways scientists are still actively studying. In fact, one of the most surprising things Voyager 1 has discovered since entering interstellar space is that this region is not calm at all. In 2023, researchers announced that Voyager 1 had detected what appears to be a persistent, low-frequency hum in the plasma of interstellar space, a kind of quiet vibration that exists even in the absence of major solar activity. The universe, it turns out, is never truly silent. There is also the matter of cosmic rays. In interstellar space, Voyager 1 is now exposed to the full force of high-energy particles streaming in from all directions, from distant supernovae, from the jets of black holes, from the violent deaths of stars hundreds of light years away. These particles pass right through the spacecraft, and they are slowly doing damage, not suddenly, not dramatically, but steadily over time, like rust on a ship, which brings us to one of the most profound and quietly heartbreaking facts in this entire story. Voyager 1 is dying not from a crash, not from an explosion, from something far more human feeling than that. It is running out of power. The spacecraft is powered by 3 radioisotope thermoelectric generators, or RTGs, which convert the heat of decaying plutonium-238 into electricity. When Voyager 1 launched in 1977, each of those generators was producing around 160 watts, roughly the same as a bright incandescent light bulb. But plutonium-238 has a half-life of about 87.7 years, meaning its output drops steadily over time. By 2024, Voyager 1's power output has fallen to around 70 watts total, and it continues to decline at roughly 4 watts per year. To keep the most essential systems alive, NASA engineers have been making incredibly difficult decisions, shutting down heaters, turning off instruments one by one, doing whatever it takes to stretch the remaining power just a little further. The mission team expects that Voyager 1 will fall silent permanently, sometime around 2025 or 2026. After nearly 50 years of sending messages across the void, the signal will stop. And that will be it. No more data, no more whispers from the edge of the known, just a silent, frozen spacecraft drifting alone through the dark between the stars, so the signal is gone. The last transmission has faded into static. Somewhere out in the interstellar dark, Voyager 1 has gone quiet. No more beeps, no more data packets crossing billions of kilometers to reach an antenna dish in a California desert, just silence. But the spacecraft itself, that little golden machine built by human hands in the 1970s, is still out there, still moving, still falling through the void at 17 kilometers every single second. And it will keep doing that for a time span so vast it makes the entire history of human civilization look like a single heartbeat. This is where the story gets truly cosmic. Because what happens to Voyager 1 after it goes silent is not a story about technology anymore. It is a story about time, about the deep, almost incomprehensible stretches of time that exist between here and the eventual end of things. And to understand it, you need to completely let go of any time scale you have ever used before. Years, centuries, even millennia, those are going to become completely useless to us in a few minutes. So let us start small. Relatively small, anyway. For the first few thousand years after Voyager 1 goes silent, very little changes outwardly. The spacecraft continues drifting through the local interstellar medium, that thin, whispering soup of ancient hydrogen and helium we talked about in Part 1. It is cold out there, extraordinarily cold. The temperature of interstellar space sits at around -270 degrees Celsius, just a couple of degrees above absolute zero, the theoretical point at which all molecular motion stops entirely. Nothing gets much colder than that anywhere in the observable universe. At these temperatures, any remaining moisture or volatile compounds on the spacecraft's surfaces would have long since frozen solid and then slowly sublimated away into the vacuum. The spacecraft's gold-anodized aluminum frame, its antenna dish, its instrument booms, all of it would be coated in a faint glaze of radiation damage. Cosmic rays punching through metal and circuitry, knocking atoms out of alignment, slowly but steadily degrading the physical structure of the spacecraft over thousands of years. But here is the thing: metal in a vacuum, with no oxygen, no moisture, no chemical reactions to accelerate decay, is extraordinarily durable. Scientists estimate that the physical structure of Voyager 1 could remain largely intact for millions of years, possibly tens of millions. The electronics would be long dead, the radioactive fuel completely decayed, the moving parts frozen solid. But the bones of the machine, the frame, the dish, the golden record, those could survive for an almost absurd length of time. And speaking of the golden record, we need to talk about it, because it is one of the most extraordinary objects ever created by our species, and its fate is tied directly to everything we are discussing. Voyager 1 carries a 12-inch gold-plated copper disc known as the Golden Record. It was assembled under the direction of Carl Sagan and a small team of scientists, artists, and thinkers who were given an almost impossible task: represent humanity to the universe, distill what we are, what we sound like, what we see, what we feel, what we value, into a single object that could survive the journey between the stars. The record contains 115 images encoded in analog format. Pictures of the Earth, of humans, of animals, of cities, of scientific diagrams. It contains sounds, the sound of wind and rain and surf, the sound of a mother's first words to her newborn child, the sounds of birds and whales and the human heartbeat. It contains greetings in 55 human languages, including ancient ones no longer spoken by any living person. And it contains music: Chuck Berry's Johnny B. Good, a Javanese court gamelan, Azerbaijani bagpipes, Bach, Beethoven, a Peruvian wedding song. Carl Sagan once said that the Golden Record was a message in a bottle cast into the cosmic ocean. And that image, a bottle floating in an ocean, is perhaps the most honest description of what Voyager 1 truly is. It is not a probe anymore. It is not a science instrument. It is a piece of us, a tiny, fragile, astonishing piece of us, drifting through the dark on the longest journey anything we have ever made has ever taken. The record itself, according to NASA, should remain playable, physically intact and theoretically decodable for at least 1 billion years. 1 billion years. To put that in perspective, 1 billion years ago, the most complex life on Earth was single-celled organisms floating in shallow seas. The continents looked nothing like they do today. The moon was closer to the Earth, the sun was slightly dimmer, and yet, if something found the golden record in that unimaginably distant future, it could still, in theory, play it, still hear the rain, still hear the heartbeat. That thought should do something to you. It does something to me every single time. Now, let us get back to the journey itself, because there is a very specific destination we need to talk about, one that most people have never heard of, and one that Voyager 1 is in a very real sense heading toward, even if it will take an almost absurd amount of time to get there after leaving the heliopause and entering interstellar space. Voyager 1 is technically still within a much larger, much more loosely defined boundary of our solar system. You see, the sun's gravitational influence does not simply stop at the heliopause. Gravity is not particles. It does not get blown back by interstellar wind. It reaches much, much further. There is a region surrounding our solar system called the Oort Cloud. And understanding the Oort Cloud is essential to understanding the true scale of what Voyager 1 is up against. The Oort Cloud is a vast spherical shell of icy bodies, comets, frozen rocks, chunks of ancient material left over from the formation of the solar system 4.6 billion years ago. It begins at a distance of roughly 2,000 astronomical units from the Sun, where 1 astronomical unit is the average distance from the Earth to the Sun, about 150 million kilometers, and it extends outward to somewhere between 50,000 and 200,000 astronomical units. At its outer edge, the Oort Cloud is almost halfway to the nearest star. Let that sink in for a moment. The outer boundary of our own solar system's gravitational reach extends almost halfway to the next star. We think of the solar system as the Sun and its 8 planets, maybe a few dwarf planets and asteroid belts. But that is just the inner city. The Oort Cloud is the countryside, the suburbs stretching out for trillions of kilometers in every direction, almost completely invisible to our telescopes, populated by trillions of icy wanderers slowly orbiting the Sun on timescales of millions of years per orbit. We have never directly observed the Oort Cloud. Not one single object confirmed to be within it has ever been directly imaged. We know it exists because of the comets it sends our way, long-period comets that come screaming into the inner solar system on trajectories so elongated they take thousands of years to complete one orbit. When astronomers trace those trajectories backward, they all seem to originate from that vast distant shell. That is our best evidence. The comets are the Oort Cloud's calling cards, and Voyager 1 is heading directly into it. At its current speed, Voyager 1 will reach the inner edge of the Oort Cloud in approximately 300 years. 3 centuries from now. That is not that long. Honestly, it is roughly the same amount of time that separates us from Isaac Newton publishing his laws of motion, and yet the spacecraft will still be completely silent by then. Dark and cold, frozen in the deep. It will take roughly 300 years to enter the Oort Cloud. And then, and this is the part that really puts things in perspective, it will take approximately 30,000 years to pass through it entirely. 30,000 years. That is twice as long as the entirety of recorded human history. When Voyager 1 finally emerges from the far side of the Oort Cloud, Homo sapiens will have been speaking, writing, building cities, making art, going to war, falling in love, and staring at the stars for roughly the same length of time as it took the spacecraft to cross that single region of space. And even then, After 30,000 years of drifting through our own solar system's outermost reaches, Voyager 1 will still not have reached another star. The nearest star to our Sun is Proxima Centauri, a small, dim red dwarf that sits about 4.2 light-years away. In terms of kilometers, that is roughly 40 trillion. At Voyager 1's current velocity of about 17 kilometers per second, it would take approximately 73,000 years to travel 1 light-year, which means reaching Proxima Centauri from here would take roughly 300,000 years. Except, and this is important, Voyager 1 is not heading toward Proxima Centauri. It is heading in an entirely different direction. The spacecraft is moving in the direction of the constellation Ophiuchus, and the nearest star along that particular path is a red dwarf called Ross 248. That is not its final destination per se. Voyager 1 will not be captured by Ross 248's gravity or do anything dramatic when it gets close, but in approximately 40,000 years, Voyager 1 will pass within about 1.6 light-years of Ross 248, a cosmic near-miss, close enough to call a neighbor by interstellar standards, and then it will keep going, past Ross 248 into the open galactic disk, further and further from the warmth and light of any star it has ever known. Now here is something that I think people do not think about enough. When we say Voyager 1 is traveling through interstellar space, it sounds serene, peaceful even, just a spacecraft floating quietly through the dark. But interstellar space is not actually peaceful. It is a war zone, a slow, invisible, relentless war zone. And Voyager 1 is right in the middle of it. The interstellar medium is threaded with magnetic fields, tangled, shifting, complex magnetic structures that are the remnants of ancient stellar winds, supernova shockwaves, and the overall rotation of the Milky Way itself. These fields do not physically push Voyager 1 around much at its scale, but they do shape the flow of cosmic ray particles, and those particles are constantly bombarding the spacecraft. High-energy cosmic rays, protons and heavier atomic nuclei accelerated to near the speed of light by some of the most violent events in the galaxy pass through Voyager 1's structure continuously. Every square centimeter of the spacecraft is hit by roughly 1 cosmic ray particle per second. Over thousands of years, this radiation slowly displaces atoms within the metal, creates microscopic structural damage, and contributes to the gradual physical degradation of the spacecraft. Add to that the occasional impact from interstellar dust grains, tiny but moving at high velocity relative to the spacecraft, and you begin to see that the journey of Voyager 1 is not a peaceful drift. It is a slow erosion, a quiet, incremental wearing away of everything that makes it recognizable as a human object. In tens of millions of years, the original sharp edges of the spacecraft structure will have been softened by micrometeorite impacts. In hundreds of millions of years, the surface material will have been significantly altered. But the core of it, the dense metal frame, will endure, changed, worn, ancient, but enduring. There is something deeply moving about that if you let yourself sit with it. We build things, and they outlast us, not just by years or generations, but by geological epochs. By the timescales of planetary evolution, Voyager 1 will still exist in some form long after every mountain on Earth has been worn flat by erosion, long after every ocean has been evaporated by a dying sun, long after our entire species has either transformed into something unrecognizable or vanished entirely from the story of the cosmos. We are made of stardust, yes, but we also make things that become part of the cosmos, things that carry our stories into the dark. And that, to me, is one of the most profound things about being human, but we are nowhere near done yet. Because we still have not talked about what Voyager 1 will actually encounter in the deep future, the galactic journey ahead, the fate of the stars it will pass, and the ultimate question: where does it end up when the universe itself begins to change around it? Now we are going to zoom out even further. And I mean that almost literally, we are going to start talking about the Milky Way galaxy as a whole, about the motion of stars through the galactic disk, and about what the night sky will look like from Voyager 1's perspective millions of years from now. If enjoying this journey, make sure to subscribe and give a like. Every day we break down the most mind-bending discoveries in astronomy, astrophysics, and cosmology. You don't want to miss. All right, take a breath, because we are about to zoom out, way out, further than most people ever think about when they look up at the night sky. We are going to pull back from Voyager 1, that tiny, silent, frozen spacecraft tumbling through the interstellar dark, and look at the bigger picture, the much, much bigger picture. We are going to talk about the galaxy, and not just what the galaxy looks like from the outside, that elegant, sweeping spiral we see in textbook images. We are going to talk about what it is like to actually be inside it, moving through it, because the Milky Way is not a static painting hanging in the sky. It is a living, churning, rotating system of hundreds of billions of stars, all of them moving, all of them pulling on each other, all of them embedded in a vast rotating disk of gas, dust, dark matter, and gravitational complexity that makes the orbital mechanics of our solar system look like a toddler's mobile. And Voyager 1, our little golden messenger, is now part of that system in a way it never was before. Because once you leave the solar system, you are no longer just orbiting the sun. You are orbiting the center of the Milky Way itself. Let us start with something that might genuinely surprise you. Our entire solar system, the sun, all its planets, every moon, every asteroid, every comet in the Oort Cloud, and yes, Voyager 1 is traveling through the galaxy. Right now, as you sit here watching this, you are moving at approximately 230 kilometers per second around the galactic center. That is roughly 828,000 kilometers per hour. You are never still. Not even for a moment. The Earth spins, it orbits the sun, and the sun hurtles through the galaxy at a speed that would take you from one side of the Earth to the other in under a minute. We complete one full orbit around the galactic center approximately every 225 million years. Astronomers call this a cosmic year, or a galactic year. The last time our solar system was in the same position in the galaxy as it is right now, the dominant life forms on Earth were early dinosaurs. The time before that, it was before complex life existed at all. We have completed just over 20 galactic orbits in the entire history of our solar system. Now, here is where things get interesting for Voyager 1. As the spacecraft drifts further and further from the sun's gravitational hold on it weakens. After tens of thousands of years after it clears the Oort Cloud, Voyager 1 will no longer be meaningfully bound to our star at all. It will become an independent traveler in the galactic disk, a free-floating object, no longer part of any solar system, subject only to the large-scale gravitational tides of the galaxy itself. At that point, Voyager 1 essentially becomes a star, not in the sense of shining or burning, obviously, but in the orbital sense. It will have its own trajectory around the galactic center, its own cosmic year, its own place in the galactic dance. Now, what does that journey through the galactic disk actually look like? What will Voyager 1 drift through over the millions of years ahead? The Milky Way's disk is not a flat, uniform structure. It is layered, textured, and full of dramatically different environments. Think of it less like a smooth lake and more like an ocean, with currents, with deep trenches, with areas of violent turbulence and areas of extraordinary calm. The region we currently occupy in the galaxy is called the Orion Arm, one of the minor spiral arms of the Milky Way, sitting between two larger arms called the Perseus Arm and the Carina Sagittarius Arm. Our neighborhood within the Orion Arm is sometimes called the local bubble, a region roughly 1,000 light-years across that was carved out by a series of supernova explosions sometime in the last 10 to 20 million years. Those explosions blasted away much of the surrounding interstellar gas and dust, leaving us in a relatively sparse, low-density pocket of the galaxy. As Voyager 1 drifts further into the interstellar medium over the coming millions of years, it will eventually leave the local bubble and enter denser, more complex regions of the galactic disk. And those regions are dramatically different environments. In some parts of the galaxy, the interstellar medium is hundreds of times denser than what Voyager 1 is currently passing through. There are molecular clouds, enormous structures of cold gas and dust, some of them spanning hundreds of light years, so dense that light cannot penetrate them. These are the nurseries where new stars are born. From the inside, a molecular cloud looks like an impenetrable darkness, a wall of shadow in every direction, lit only faintly by the distant glow of stars beyond the cloud's edges. Voyager 1, drifting through such a cloud millions of years from now, would encounter a completely different kind of interstellar environment. More particles, more dust, more chemical complexity. The hydrogen atoms that form inside molecular clouds can bond together into molecules, hydrogen gas, carbon monoxide, water ice, creating a chemistry that is alien compared to the sparse atomic plasma of the region we currently inhabit. It would not stop the spacecraft. Nothing is dense enough in space to physically stop something moving at the speeds Voyager 1 is traveling, but it would leave its mark, a slow accumulation of molecular material on the spacecraft's surfaces, a gradual frosting of ancient stardust on the golden record. There is also the question of stellar encounters. Over millions and tens of millions of years, Voyager 1 will pass relatively close to other stars. Not crashingly close, the odds of an actual collision are essentially zero, given how much empty space exists between stars, even in a galaxy as populated as the Milky Way, but close enough by cosmic standards that the gravitational influence of those stars will nudge the spacecraft's trajectory, slightly, incrementally. Over deep time, these nudges accumulate, and the path of Voyager 1 becomes impossible to predict with any precision. We can, however, make some estimates about specific close approaches in the near-term future, cosmically speaking. We already mentioned that in approximately 40,000 years, Voyager 1 will pass within about 1.6 light-years of Ross 248, a small red dwarf star about 10.3 light-years from Earth today. After that flyby, the spacecraft continues into the deeper galactic disk. Then, in approximately 300,000 years, scientists have calculated that Voyager 1 will pass relatively close to another star system. The details of encounters further out than this become increasingly uncertain, because the precise motions of stars over hundreds of thousands of years involve too many variables to predict exactly. Stars themselves move. The galaxy is not static. Every calculation has an error bar that grows wider the further into the future you project. But the general picture is clear. Voyager 1 will spend millions of years drifting through a galaxy full of stars, occasionally nudged by their gravity, slowly being worn down by radiation and dust, carrying its golden record through neighborhoods of the Milky Way that no human being will ever see with their own eyes. And while we are thinking about the Milky Way, let us talk about something that is going to dramatically change the galaxy, and therefore Voyager 1's long-term environment. Over the next few billion years, the Milky Way is on a collision course. Not with a small galaxy, not with a dwarf satellite, but with Andromeda. The Andromeda galaxy, also known as Messier 31, is our nearest large galactic neighbor. It is a spiral galaxy roughly 2.5 million light-years away, and it is heading toward us at approximately 110 kilometers per second, which means that in approximately 4.5 billion years, give or take a few hundred million, The Milky Way and Andromeda will collide in one of the most spectacular and catastrophic events in the history of this region of the cosmos. Now, when people hear the word collision, they imagine something like two trains smashing into each other. But a galactic collision is not like that at all. Remember, galaxies are mostly empty space. The distance between stars is so enormous that even when two galaxies merge, the actual chance of any individual stars physically colliding is almost vanishingly small. What happens instead is a gravitational catastrophe. The two galaxies tear each other apart, disrupt each other's spiral structures, fling stars out into intergalactic space, and over hundreds of millions of years, gradually merge into a single, larger, irregular galaxy. Astronomers have even given this merged future galaxy a name, Milkomeda, or sometimes Milkdromeda. Neither name is particularly elegant, but the concept is breathtaking. During the merger, the night sky, if there is anything around with eyes to see it, will be transformed beyond recognition. The familiar band of the Milky Way that arcs across our night sky will be replaced by something far more dramatic, a chaotic blaze of new star-forming regions triggered by the collision of gas clouds, brilliant streams of stars stretching across the sky, a galactic structure unlike anything that has existed in this part of the universe for billions of years, and Voyager 1. Somewhere in all of that chaos, it is still drifting, silent, frozen, ancient, a relic from an era so far in the past that no trace of human civilization or of Earth itself would remain recognizable. Just this small, golden-winged machine tumbling through the gravitational upheaval of a cosmic collision on a scale beyond any human frame of reference. There is something I want to pause on here for a moment, because I think it is important. When we trace Voyager 1's path through billions of years of future time, we are inevitably also tracing the fate of everything we know and love. Earth, the Sun, life, civilization. The Sun is a middle-aged star. It formed about 4.6 billion years ago, and it has roughly another 5 billion years of hydrogen-burning life ahead of it. But as stars age, they change. In about 1 billion years from now, a relatively short time in the grand cosmic scheme, the Sun will have grown about 10% brighter. That might not sound dramatic, but it is enough to begin evaporating Earth's oceans. The planet will become increasingly hot, increasingly hostile to the complex life that currently covers its surface. In about 5 billion years, the Sun will exhaust the hydrogen in its core and begin to expand into what astronomers call a red giant. It will swell outward, growing hundreds of times its current diameter, potentially engulfing Mercury, Venus, and possibly Earth itself. The inner solar system will be sterilized. What was once the cradle of human civilization will become part of a star. Voyager 1 will be nowhere near any of this. By that point, it will be thousands of light years away, a nomad of the galactic disk, having long since lost any meaningful connection to the star that launched it. In a profound sense, Voyager 1 will outlive the Sun. It will outlive Earth. It will outlive every trace of the world that made it, and that is where the story gets quiet again. Because after the Sun dies, after the Milky Way and Andromeda merge into Milkomeda, after billions and billions of years have carved away every familiar landmark in this corner of the cosmos, Voyager 1 will still be there, different, ancient, worn, but there. What happens to it in those deep future epochs, when the universe itself begins to change in fundamental ways, is something we are going to get into very soon. Because the story does not end with a galactic merger or the death of our star. The story of Voyager 1 extends all the way to the edge of what physics currently tells us is possible. There is a concept in physics called the Stellar Era. It is not a term you hear thrown around in everyday conversation, but once you understand what it means, you will never look at the night sky quite the same way again. The Stellar Era is the age of stars, the period in cosmic history, our current period, during which the universe is filled with burning, shining, hydrogen-fusing stars. It began a few 100 million years after the Big Bang, when the first stars ignited in the primordial dark, and it will end, according to our best current understanding of stellar physics, in roughly 100 trillion years from now. 100 trillion years. Our universe is currently about 13.8 billion years old, which means we are not even 1/10 of the way through the Stelliferous Era. The age of stars has barely begun. We are, cosmically speaking, living at the very dawn of the universe's stellar life. And Voyager 1, that silent, frozen relic tumbling through the galactic dark, will be there for all of it, every single year of those 100 trillion, drifting, enduring, witnessing in its own silent way the slow transformation of the cosmos from a blazing garden of stars into something altogether different. Let us walk through what that actually looks like. For the first few billion years after its launch, the period we are in right now, and the several billion years ahead, the universe will look broadly similar to how it looks today. Galaxies will continue forming stars, supernovae will continue exploding and seeding the interstellar medium with heavy elements, new solar systems will continue coalescing from clouds of gas and dust, life, perhaps, will continue emerging on worlds scattered across the cosmos, worlds we have not yet found around stars we have not yet named. But even within this relatively stable era, change is coming. Slow, inevitable, thermodynamic change. The key thing to understand is that star formation is not a renewable process. When a star forms, it uses up a portion of the available gas and dust in its vicinity. When it dies, whether as a gentle white dwarf, a violent supernova, or a neutron star, it returns some of that material to the interstellar medium, but not all of it. Some fraction is locked away permanently in the stellar remnant, a white dwarf, a neutron star, a black hole. Over time, the total amount of raw material available to form new stars decreases. The galaxy slowly runs out of the ingredients it needs to keep making them. Astronomers believe that the rate of star formation in the Milky Way has already been declining for several billion years. We are past the universe's peak of stellar productivity. The cosmic baby boom, so to speak, is over. What we see now is a galaxy in the long, slow process of winding down. In about 1 trillion years, which is roughly 70 times the current age of the universe, the last new stars will form in the Milky Way. After that, no new stars will ignite. The galaxy will still contain stars. Red dwarfs, which are by far the most numerous type, can burn for trillions of years, but they will be an aging population, a generation that will not be replaced. Now, red dwarfs deserve a moment of special attention here because they are extraordinary objects that most people dramatically underestimate. A red dwarf is a small, cool, dim star, typically between about 8% and 50% the mass of our Sun. They shine with a reddish or orange glow, faint enough that not a single red dwarf in the entire universe is visible to the naked eye from Earth, despite the fact that they make up roughly 70 to 75% of all stars in the Milky Way. They are everywhere, these quiet little stars, burning so slowly and so efficiently that the most massive of them will not exhaust their fuel for over 10 trillion years. The smallest red dwarfs, tiny, barely stars objects just above the minimum mass needed to sustain hydrogen fusion, may burn for up to 100 trillion years or more. By comparison, our Sun will live for about 10 billion years total. A small red dwarf will outlive our Sun by a factor of 10,000. These stars will be the last lights in the universe, long after every Sun-like star has swelled into a red giant, shed its outer layers, and collapsed into a cooling white dwarf. Long after every massive star has exploded and left behind neutron stars and black holes, the red dwarfs will still be burning, quietly, patiently, scattered across a galaxy that has grown darker and emptier with each passing billion years, and somewhere out in that darkening galaxy, Voyager 1 drifts on. Let us think about what the universe actually looks and feels like during this long twilight period, the late Stelliferous Era, say, 50 to 100 trillion years from now. The night sky, viewed from any hypothetical vantage point, would be dramatically different from what we see today. The brilliant blue-white stars, the massive, short-lived giants that currently make our galaxy glow with fierce white light, would be long gone. No more supernovae lighting up the arms of the galaxy, no more brilliant stellar nurseries blazing in the infrared. The galaxy would be populated almost entirely by dim, reddish stars, glowing like cooling embers rather than roaring flames. The overall light level in the cosmos would be a tiny fraction of what it is today. Galaxies, those that have not merged into giant elliptical structures, would be dim, reddish smudges, barely distinguishable from the darkness around them. The cosmic microwave background radiation, that faint glow left over from the Big Bang, which currently has a temperature of about 2.7 degrees Kelvin, will have cooled further, stretched by the ongoing expansion of the universe to even longer wavelengths, even lower temperatures. The universe will be getting colder, darker, and quieter with each passing trillion years. And the expansion of the universe itself will have continued, indeed accelerated. We know from observations of distant supernovae and the cosmic microwave background that the universe is not just expanding, it is expanding at an increasing rate, driven by a mysterious force called dark energy. Over trillions of years, this accelerating expansion will push distant galaxies further and further away until they recede faster than light can travel between us and them. One by one, galaxies beyond our local group will disappear below the cosmic horizon, not destroyed, but rendered permanently unreachable and invisible, carried away by the expansion of space itself. The observable universe will shrink, not because there is less of it, but because light from increasingly vast regions will never reach us again. The cosmos will become, in a very real sense, lonelier. Now, through all of this, through the slow dimming of the stellar population, through the expansion of the cosmic horizon, through the gradual silencing of the galaxy. Voyager 1 continues its drift. By the time the last red dwarfs are approaching the end of their lives, somewhere around 100 trillion years from now, Voyager 1 will have completed an almost incomprehensible number of orbits around the galactic center. It will have passed through regions of the galaxy that our greatest telescopes today cannot even resolve into individual structures. It will have drifted through stellar nurseries and stellar graveyards, through ancient molecular clouds and the swept-clean remnants of exploded stars. Its physical structure by this point will have been altered significantly by billions of years of cosmic ray bombardment and micrometeorite impacts. The original sharp geometry of its antenna dish will have been softened, worn, pitted. The gold plating on various surfaces will have been eroded and redeposited in ways that make the original design barely recognizable up close. But here is the thing: in the void of space, with no atmosphere, no liquid water, no chemical weathering, the decay is extraordinarily slow. The core metallic structure could still be largely intact. The golden record, protected by its aluminum cover, could still be physically present, a thin copper disc, slightly degraded, but carrying its encoded images and sounds and greetings into a cosmos that has changed beyond all recognition since those messages were first pressed into its surface. There is a term used in long-range cosmic forecasting called proton decay. Now, this is where we enter genuinely uncertain scientific territory, and I want to be clear about that. Proton decay is a theoretical prediction from certain extensions of the standard model of particle physics, specifically from grand unified theories that attempt to unite the strong nuclear force with the electroweak force. The idea is that protons, the fundamental particles that make up the nuclei of atoms, and therefore the nuclei of everything, including Voyager 1, are not actually stable forever. They have an extremely long but finite lifespan. If protons do decay, the current experimental lower bound on their half-life is at least 10 to the 34th years. That is a 1 followed by 34 zeros, an almost literally incomprehensible number. For context, the current age of the universe is about 10 to the 10th years, so proton decay, if it occurs, operates on timescales roughly 10 trillion times longer than the current age of the cosmos. If proton decay is real, then eventually, on these unimaginable timescales, every atom of Voyager 1 would dissolve. The copper in the golden record, the aluminum in the frame, the gold in the plating. Every proton would eventually release its energy in a faint spray of lighter particles, and the spacecraft would simply cease to exist as matter. Not with a bang, not dramatically, just a slow, quantum-level evaporation of everything it is made of, spread across timescales that make the current age of the universe look like a Planck instant. But here is the honest scientific caveat. We do not actually know if protons decay. Every experiment designed to detect proton decay, including massive underground detectors filled with thousands of tons of ultra-pure water, has so far come up empty. Proton decay may be real, but operating on timescales even longer than our best theories predict, or it may not happen at all. The standard model of particle physics, without modification, actually predicts protons are stable indefinitely. We genuinely do not know, and I love that we do not know, because it means the story of Voyager 1, the question of its ultimate fate, touches on some of the deepest, most unresolved questions in all of physics. What is matter at its most fundamental level? Is it permanent or temporary? Does the universe trend toward dissolution or toward some kind of eternal frozen persistence? These are not rhetorical questions, they are live scientific debates, and they matter enormously for understanding what happens to everything, including our little golden spacecraft, at the very end of time. But before we get to the absolute end of things, there is one more extraordinary chapter in the Stelliferous Era that we need to talk about, something that will happen long before the last red dwarfs expire. Something that involves black holes and the slow cannibalization of the galaxy itself. You see, at the center of almost every large galaxy, including our own Milky Way, sits a supermassive black hole. Ours is called Sagittarius A star, and it has a mass of about 4 million times that of our Sun. It is not particularly active right now. In astronomical terms, it is relatively quiet, occasionally snacking on passing gas clouds but not doing anything dramatic. But over billions and trillions of years, as the galaxy evolves and stars slowly spiral inward due to gravitational interactions, more and more material will eventually find its way into the galactic center. Black holes grow, slowly over cosmic timescales, but they grow. And the gravitational dynamics of a galaxy over trillions of years are such that stars can be kicked out into intergalactic space, a process called gravitational evaporation, while others spiral inward. Over timescales of about 10 to the 19 to 10 to the 20 years, gravitational interactions between stars will cause most of the stars remaining in the galaxy to either be ejected entirely into the void between galaxies or to spiral down into the central black hole. The galaxy will dissolve, not explosively, not dramatically, just gravitationally over unimaginable spans of time, stars drifting away one by one, the structure of the galaxy slowly dissipating like smoke in a gentle wind. And Voyager 1, it could be one of the objects that gets ejected. A chance gravitational encounter with a passing star, even a very distant, very weak encounter, accumulated over billions of years, could give the spacecraft just enough of a nudge to send it out of the galaxy entirely, into the vast, dark, cold, intergalactic void. the space between galaxies, which is far emptier than anything within a galaxy, where the nearest star is not light years away, but millions of light years away, or it could spiral inward, toward the galactic center, toward the black hole. Both possibilities are real, both are on the table, and both lead to extraordinary endings, which we are going to explore in detail very soon. Right now, though, I want to pause and appreciate something, because I think it is easy, when you are deep in the numbers, trillions of years, quantum decay, galactic collisions, to lose sight of what this all actually means on a human level. Voyager 1 was built by people, ordinary, extraordinary people. Engineers who worked long hours in buildings in California in the 1970s, scientists who argued over instrument designs and trajectory calculations, a small team of dreamers who put human voices and music and the sound of rain onto a golden disc and sent it into the dark, not because they expected it to be found, but because the act of sending it said something true about who we are. We are a species that reaches. We reach even when we cannot see what we are reaching toward. We put messages in bottles and throw them into oceans we will never cross. We build machines and send them to places we will never go. We ask questions whose answers we will never live to hear. And in doing so, we become, in the most literal physical sense, part of the cosmos, not just observers of it, but participants, contributors. Voyager 1 is not just a spacecraft anymore. It is a piece of the universe that carries the fingerprints of one particular planet, one particular moment, one particular species that looked up at the stars and decided to reach back. That is not nothing. That is everything. The last star goes out, not with an explosion, not with a shockwave rippling across the galaxy, just a slow, quiet dimming, a red dwarf, somewhere in what used to be the Milky Way, finally exhausting the last of its hydrogen fuel and collapsing inward into a cold, dark sphere of degenerate matter. No fanfare, no witness, just the universe becoming a little darker than it was before. This moment, whenever it comes, roughly 100 trillion years from now, marks one of the most profound transitions in the entire history of the cosmos, the end of the Stelliferous Era, the end of the age of stars. Everything that comes after is something different, something quieter, something our human minds evolve to process. The timescales of seasons and lifetimes and civilizations are genuinely not built to intuitively grasp, but we are going to try anyway, because Voyager 1 is still out there, still drifting, and the universe it finds itself in, from this point forward, is almost unrecognizable compared to the one that launched it. Welcome to the Degenerate Era. The Degenerate Era is the name cosmologists give to the long, dark period following the death of the last stars. It spans from roughly 100 trillion years after the Big Bang to somewhere around 10 to the 40th years, a number so large that writing it out in full would require more zeros than there are atoms in the observable universe. During this era, the universe is not empty, but what fills it is nothing like what fills it today. The primary inhabitants of the Degenerate Era are the remnants of dead stars, white dwarfs, the dense, slowly cooling cores left behind when suns-like stars exhaust their fuel and shed their outer layers, neutron stars, the city-sized, extraordinarily dense objects left behind by the supernova explosions of massive stars, spinning sometimes hundreds of times per second, radiating energy as radio waves and X-rays, until even that energy slowly bleeds away, and black holes, the gravitational endpoints of the most massive stellar deaths, objects so dense that not even light can escape their pull. These are the inhabitants of the Degenerate Era, not burning stars, not illuminated worlds, just cold remnants slowly cooling, slowly radiating away the last of their energy into an increasingly frigid cosmos. Let us talk about white dwarf for a moment, because they are going to be the dominant objects in the universe for an extraordinarily long time, and they are genuinely fascinating. When a star like our Sun reaches the end of its life, In about 5 billion years, as we discussed, it will expand into a red giant, fusing helium in its core and puffing its outer layers out into space. Eventually, the outer layers will be expelled entirely, forming a beautiful shell of glowing gas called a planetary nebula. And at the center of that nebula, left behind like a cooling ember in the ash of a fire, will be the star's core, a white dwarf. A white dwarf is roughly the mass of the Sun compressed into a sphere about the size of the Earth. The density is almost incomprehensible. A single teaspoon of white dwarf material would weigh roughly 5 tons on Earth. The surface temperature of a newly formed white dwarf can reach over 100,000 degrees Celsius. It shines brilliant white, hot and fierce, but it has no fuel left. It is not fusing anything. It is simply radiating away the heat it accumulated over billions of years of stellar life, and it cools slowly, incredibly slowly. The cooling timescale for a white dwarf is so long that in the current age of the universe, 13.8 billion years, not a single white dwarf anywhere in the cosmos has had enough time to cool completely. They are all still warm. The universe is not old enough yet to have produced even one cold white dwarf, but given enough time, and in the Degenerate Era, time is the one thing the universe has in abundance. White dwarfs will cool to match the ambient temperature of the universe around them. They will become what physicists call black dwarfs, cold, dark, inert spheres of crystallized carbon and oxygen drifting silently through the void. Objects that emit essentially no radiation whatsoever, invisible against the darkness of the cosmos, detectable only by their gravitational influence. The transition from white dwarf to black dwarf is estimated to take somewhere between 10 to the 15th and 10 to the 25th years, depending on the mass of the original star. In any case, timescales utterly beyond any human reference point. Now, here is something beautiful that I want you to hold in your mind for a moment. The carbon in some of these cooling white dwarfs will, under the extraordinary pressures of their interiors, crystallize, literally crystallize. The carbon atoms will lock into a face-centered cubic lattice structure, the same arrangement of atoms found in diamonds. Some white dwarfs, as they cool, will essentially become giant diamonds, spheres of crystallized carbon, roughly the size of the Earth, drifting silently through the dark of the Degenerate Era universe, a diamond the size of a planet, floating in the void, cold and dark and invisible, carrying within its crystal structure the compressed history of a star that once burned for billions of years. That is real, that is actual physics, and it is one of the most quietly extraordinary things I have ever learned. So what is Voyager 1 doing during all of this? By the time the Degenerate Era begins, 100 trillion years after launch, Voyager 1 has been traveling for a length of time roughly 7,000 times longer than the current age of the universe. If you tried to represent the entire history of the cosmos up to now as a single day, Voyager 1's journey to this point would represent about 19 years of continuous travel. It has drifted through regions of the galaxy that no longer exist in any recognizable form. It has passed through the aftermath of the Milky Way-Andromeda merger, through the slow gravitational dissolution of what became Milkomeda, and out the other side, possibly into the intergalactic void, possibly still loosely associated with whatever dark, cooling remnants remain of our galactic neighborhood. The spacecraft itself, by this point, has been altered by 100 trillion years of cosmic ray bombardment. Every surface exposed to the interstellar and intergalactic medium has accumulated radiation damage on a scale that is genuinely difficult to calculate with any precision. Theoretical models of radiation damage to metals in space suggest that the crystalline structure of the aluminum and gold and copper that make up Voyager 1 would be significantly disrupted. Atoms knocked out of their lattice positions, replaced, shifted over billions upon billions of years of high-energy particle impacts. And yet, and this is the part that I keep coming back to, the fundamental matter is still there. The atoms have not gone anywhere. A copper atom displaced from its original position in the golden record substrate is still a copper atom. The information encoded in the record, the physical grooves that represent sound waves, the images encoded in the radial variations, may be degraded, may be partially erased by radiation and micro-impacts, but the material itself persists. Voyager 1 in the Degenerate Era is no longer recognizable as a spacecraft. It is an artifact, a relic, an object whose origin and purpose would be, to any hypothetical intelligence that encountered it, deeply mysterious, because all context has been lost. The star it came from has been dead for billions of years. The planet that built it has been consumed by that star's expansion. The civilization that designed it left no other traces visible across the distances involved. It is just a thing. An ancient, strange, slightly irregular object made of unusually pure metals, drifting through a cold, dark universe, carrying within its atomic structure the ghost of an intention it can no longer communicate. Now let us talk about something that will dramatically reshape the landscape of the Degenerate Era universe and potentially determine Voyager 1's ultimate fate: black holes. During the Degenerate Era, black holes become increasingly important players in the universe. As stars die and leave their remnants, as galaxies dissolve, and their stellar populations either drift away into intergalactic space or spiral inward, the supermassive black holes at galactic centers gradually accumulate more and more mass. They grow, slowly but relentlessly, and they do something else too, something that, when Stephen Hawking first proposed it in 1974, seemed so counterintuitive that many physicists initially rejected it. Black holes evaporate. This process is called Hawking radiation, and it is one of the most profound predictions in theoretical physics, sitting right at the intersection of quantum mechanics and general relativity, the two great frameworks of modern physics that we have still not fully unified. The basic idea is this: near the event horizon of a black hole, quantum fluctuations in the vacuum of space cause pairs of particles to spontaneously pop into existence. In most of space, these particle pairs immediately annihilate each other and disappear. But right at the edge of a black hole's event horizon, sometimes one particle of the pair falls in while the other escapes. The escaping particle carries away a tiny amount of energy, and because energy and mass are equivalent, as Einstein showed us, the black hole loses a tiny amount of mass with each particle that escapes. The rate of Hawking radiation is inversely proportional to the mass of the black hole. Small black holes evaporate quickly. Supermassive black holes evaporate incredibly slowly. The supermassive black hole at the center of our galaxy, Sagittarius A star, with 4 million solar masses, would take approximately 10 to the 87th years to evaporate completely via Hawking radiation. That is a number so large that I am genuinely not sure any analogy I could offer would make it feel real, but eventually, even the largest black holes evaporate, and when they do, the final moment of their evaporation is not quiet. The smaller a black hole gets, the faster it radiates, in a feedback loop that ends in a brief, brilliant flash of high-energy radiation, a final explosion that releases, in a fraction of a second, the last of the energy that the black hole has been holding since it formed. Perhaps trillions upon trillions of years earlier, the last black holes will evaporate somewhere around 10 to the 92nd to 10 to the 100th years after the Big Bang. After that, there are no more black holes. The universe has lost one of its most dramatic and powerful structures, and what remains is something almost incomprehensibly sparse and dark. Let us zoom back into Voyager 1 during the era of black hole evaporation. This is so far into the future that assigning specific conditions to the spacecraft becomes more speculative, but we can reason from physics. By this point, somewhere between 10 to the 40th and 10 to the 100th years, Voyager 1 has been subject to the long-term gravitational dynamics of whatever large-scale structures remain. If it was ejected from the galactic remnant billions of years earlier, it is now somewhere in the intergalactic void, the space between galactic remnants, in a universe that is almost entirely dark. The ambient temperature of the universe by this point is extraordinarily close to absolute zero. The cosmic microwave background radiation has been stretched by expansion to wavelengths so long and temperatures so low that it is barely distinguishable from nothing. The environment around Voyager 1 is essentially the closest thing to true emptiness that can physically exist. A particle density so low that the spacecraft might travel for extraordinary distances without encountering so much as a single hydrogen atom. The magnetic fields of the old interstellar medium are long since dissipated. Cosmic rays, which depended on active astrophysical processes like supernovae and active galactic nuclei, have largely ceased, because the processes that generated them have ended. In a strange and counterintuitive way, this is actually the most physically gentle environment Voyager 1 has experienced since it left the Earth. Less radiation, less particle bombardment, less erosion. The spacecraft, or what remains of it, drifts through a universe that has finally, in a sense, calmed down. But calm does not mean eternal. And this is where we need to address something that I mentioned earlier and promised to return to: the question of proton decay. Because whether or not protons are stable over truly cosmological timescales is the single most important variable in determining Voyager 1's ultimate fate. If protons do not decay, if the standard model is correct that they are fundamentally stable, then the matter composing Voyager 1 could, in principle, last essentially forever, worn, altered, eroded, restructured by billions of years of radiation, but still matter, still copper and aluminum and gold, still atoms with nuclei and electrons, still physical stuff occupying physical space. In this scenario, Voyager 1, or its atomic remnants, persists into the absolute deep future of the universe, long past the evaporation of the last black hole, drifting through a cosmos that has become as close to nothing as something can get. But if protons do decay, if some extension of the standard model is correct, and protons have a finite, if enormously long, lifespan, then somewhere around 10 to the 34th to 10 to the 40th years, the protons within Voyager 1 begin to spontaneously decay into lighter particles, positrons and pions, which themselves decay rapidly into photons and neutrinos. One by one, atom by atom, the copper dissolves, the aluminum dissolves, the gold dissolves, the golden record dissolves. Everything that was once Voyager 1 becomes a thin haze of photons and leptons, spreading outward at the speed of light into an increasingly dark and empty universe. The sound of rain on the golden record, the human heartbeat, Chuck Berry's guitar, all of it converted back into energy, returned to the cosmos from which it came. There is something in that image that I find both heartbreaking and strangely beautiful, because in a sense, it is just matter doing what matter does, transforming. The atoms in Voyager 1 were forged in the hearts of ancient stars billions of years before the Earth existed. They became rock, and then metal, and then a spacecraft, and then a relic, and then perhaps pure energy again, part of the endless cycling of the cosmos. We are all, in the end, borrowed stardust. And eventually, the loan comes due. But here is the thing. Even if every atom of Voyager 1 eventually dissolves, even if proton decay is real, and every physical trace of the spacecraft eventually converts to radiation, something remains. Because the photons released by that decay travel outward at the speed of light in all directions. They carry, encoded in their energy levels and their timing, the faintest possible imprint of the structure that released them. Not readable, not decodable by any technology we can imagine, but physically real, causally connected to everything Voyager 1 ever was in physics, information is extraordinarily difficult to truly destroy. The universe keeps its records even when no one is reading them. Let's step into the absolute deep future, past proton decay, past black hole evaporation, into the dark era, the final epoch of the universe as we understand it. A place so remote in time that the numbers involved stop feeling like numbers and start feeling like philosophy. And I want to ask you something as we head there, because I think it matters. Not just scientifically, but personally. What does it mean for something to matter if it eventually ends? What does it mean to reach across the cosmos with a golden record if trillions of years from now, even the atoms of that record will dissolve into light? There is a moment in every long journey where the landscape becomes completely unrecognizable, where every familiar landmark has long since disappeared behind the horizon, and what lies ahead bears no resemblance to anything you have ever seen or imagined, where the traveler, if there is one, can no longer orient themselves by anything they knew at the start. Voyager 1 reached that moment a long time ago in cosmic terms, but we are about to reach it too, right now, together, because what comes after the Degenerate Era, after the last white dwarfs have cooled to black, after the last neutron stars have spun down to silence, after the last black holes have evaporated in their final brilliant flashes, is something that does not have a good analogy in human experience. It does not look like anything, it does not sound like anything, it barely even qualifies as a place in any meaningful sense. Cosmologists call it the Dark Era, and it is by an almost incomprehensible margin the longest chapter in the universe's story. Let us establish some orientation, even though the numbers involved will quickly outrun any intuition you have. The current age of the universe, approximately 13.8 billion years. The end of the Stelliferous Era, the last star, approximately 100 trillion years. The end of the Degenerate Era, the last black hole evaporates, approximately 10 to the 100th years. That is a 1 followed by 100 zeros. Mathematicians call this number a googol. Yes, that is where the name of the search engine comes from. The Dark Era begins after that, after the googol, after every star is dead, every white dwarf has cooled to black, every black hole has evaporated. What remains is a universe containing, in any given enormous volume of space, essentially nothing but the occasional dark remnant. A black dwarf here, a rogue neutron star there, perhaps some subatomic particles drifting freely, all of it separated by distances so vast they beg a description, in a universe that has expanded to a size so enormous that the concept of distance itself starts to break down. The temperature of the universe in the Dark Era is so close to absolute zero that the difference is, for most practical purposes, indistinguishable from nothing. The expansion of the universe continues, driven by dark energy, stretching the fabric of space in every direction, pushing whatever sparse remnants remain further and further apart with every passing moment. This is the universe Voyager 1, or whatever remains of it, inhabits in the Dark Era. Now, I want to be genuinely honest with you here, because I think intellectual honesty is one of the most important things a science communicator can offer. The physics of the Dark Era is, by necessity, deeply speculative, not because physicists are guessing, but because the observational evidence we could use to constrain our models simply does not exist yet, and may never exist. We are extrapolating known physical laws across timescales so vast that even tiny uncertainties in those laws compound into enormous uncertainties in predictions. What I am about to describe is our best current theoretical understanding, but I want you to hold it with appropriate humility as a framework for thinking, a scaffolding of ideas rather than established fact. The universe at 10 to the 100th years is not something anyone will ever directly observe. It is something we reason toward from the physics we know, extended as carefully and honestly as we can into the territory we do not. With that said, let us go there. The Dark Era is characterized above all else by one thing: the dominance of quantum mechanics over everything else. In the Stelliferous Era, our era, the universe is dominated by the large-scale physics of gravity and thermodynamics. Stars form, burn, explode. Galaxies orbit, merge, dissolve. These are classical, large-scale processes operating on scales of light years and solar masses. Quantum effects exist. Obviously, they are responsible for the nuclear fusion that powers the stars, among other things, but they play a supporting role to the grand classical drama of cosmic structure. In the Dark Era, all of that classical drama is over. The stars are gone, the galaxies are gone, the black holes are gone. What remains are individual particles, electrons, positrons, photons, neutrinos, separated by unimaginable distances, interacting so rarely that the universe operates more like a quantum system than a classical one. The universe, in its old age, becomes more like a quantum vacuum than a classical cosmos. And in a quantum vacuum, strange things happen, slowly, rarely, but inevitably. One of the most extraordinary predictions of quantum field theory is something called vacuum decay. It is a concept that sits at the boundary between theoretical physics and what sounds, frankly, like science fiction. But it is real physics, taken seriously by serious physicists, and it has potentially enormous implications for the ultimate fate of everything, including Voyager 1. Here is the idea. The vacuum of space, what we think of as empty space, is not truly empty at the quantum level. It has an energy called the vacuum energy or zero-point energy, and crucially, this energy may not be at its absolute minimum possible value. Our vacuum may be what physicists call a false vacuum, a metastable state, sitting in a kind of energy valley, stable enough to persist for an extraordinarily long time, but not the lowest possible energy state the universe could be in. If our vacuum is a false vacuum, then quantum tunneling, the quantum mechanical process by which particles can pass through energy barriers that classical physics says they cannot cross, could, at some point, trigger a transition to a lower energy state. This transition would begin at a single point in space and expand outward at the speed of light in all directions as a bubble of true vacuum. A region of space with fundamentally different physical laws sweeps through the cosmos. Everything the bubble wall passes through is instantly converted to the new vacuum state. Atoms as we know them would cease to exist. The fundamental constants of nature, the strength of the electromagnetic force, the masses of particles, perhaps even the dimensionality of space, could change within the bubble. It would be the end of physics as we know it, expanding at the speed of light, absolutely unstoppable, and because it travels at the speed of light, utterly undetectable before it arrives, no warning, no preparation. Just the universe rewriting its own rules from the inside out. Now, the critical question. Has vacuum decay already happened somewhere in the observable universe? We have no evidence that it has. And the fact that our vacuum has persisted for 13.8 billion years without decaying suggests that, if it is a false vacuum, it is an extremely stable one. The tunneling rate is extraordinarily low. It could persist for times far longer than the current age of the universe, possibly longer than the Dark Era itself, but possibly not. And if vacuum decay does occur, if a bubble of true vacuum is nucleated anywhere in our observable universe, or has already been nucleated in some region beyond our cosmic horizon, then the fate of Voyager 1 and of everything else is decided in an instant, not gradually, not gently, instantaneously. There is a strange kind of mercy in that if you want to find one. No slow erosion, no gradual dissolution, just a boundary, traveling at the speed of light, and then whatever the new physics is. But let us set vacuum decay aside for a moment and return to the scenario where the physics we know continues to apply indefinitely. Because even without such a dramatic intervention, The Dark Era has its own extraordinary processes playing out across its vast timescales. One of the most mind-bending is something called quantum tunneling on a cosmological scale. We are used to thinking of quantum tunneling as a process that operates at the subatomic level, an electron tunneling through a barrier in a transistor, a proton tunneling through a nuclear potential well in stellar fusion. But quantum mechanics does not have a size limit. The equations apply at all scales. The probability of tunneling for large, complex objects is almost incomprehensibly small, but it is not zero. Over sufficiently enormous timescales, the kinds of timescales that exist within the Dark Era, even large-scale quantum events become possible, in principle. One that physicists have calculated semi-seriously and semi as a thought experiment is the spontaneous quantum tunneling of dead matter into new configurations. Given enough time, and we are talking about timescales that make the Dark Era itself look brief, there is a non-zero probability that any given collection of atoms could quantum tunnel into a different arrangement, a more ordered arrangement, conceivably even a living arrangement. This is the basis for what is sometimes called the Boltzmann brain paradox, the idea that in a universe of infinite time, random quantum fluctuations could spontaneously assemble conscious, thinking entities out of the thermal noise of the vacuum, not through any process of evolution or design. Just statistical inevitability, given enough time. This is not science fiction. It is a genuine problem in theoretical cosmology that physicists take seriously. Not because Boltzmann brains are likely, but because their apparent inevitability in certain cosmological models reveals something important about those models. If your theory of the universe predicts that random conscious observers should vastly outnumber evolved ones, something is probably wrong with your theory. I bring this up not to claim that something bizarre will necessarily happen to Voyager 1 in the deep future, but to illustrate the extraordinary nature of the timescales we are dealing with. In the Dark Era, the universe is so old and time is so abundant that concepts we normally reserve for the subatomic scale start bleeding into the macroscopic. The boundary between the probable and the improbable dissolves, given enough time. Now, let us get specific about Voyager 1 again, because we have been in the abstract for a while, and I want to bring this back to the physical. In the Dark Era, assuming proton decay has not occurred, or occurs at the very upper end of theoretical predictions, Voyager 1's physical remains drift through a universe that is, to all practical purposes, empty. The spacecraft is no longer a recognizable object in any engineering sense. It is a cluster of atoms, primarily aluminum, copper, gold, and various other metals and materials, held together by electromagnetic forces, with no internal energy source, no moving parts, no thermal gradient of any significance. The temperature of the object will have equalized with the ambient temperature of the universe, a fraction of a degree above absolute zero. Every atom in the spacecraft is as close to its lowest energy state as quantum mechanics allows. The electrons are in their ground states. The nuclei are cold. Nothing moves except at the quantum level. And yet, something persists in the structure, because the arrangement of atoms in the spacecraft is not random. It was arranged by intelligence with purpose. The grooves in the golden record are not random patterns, they encode information. That information, in a deep physical sense, is still there as long as the physical structure remains intact. Degraded, certainly, partially erased by billions of years of radiation, but not entirely gone. There is a concept in information theory called Landauer's principle, which states that information has a physical reality, that erasing a bit of information requires a minimum amount of energy, and that information is therefore, in a fundamental sense, a physical quantity tied to the thermodynamic state of matter. If that principle holds all the way to the bottom, and most physicists believe it does, Then the information encoded in Voyager 1 is part of the physical state of the universe as long as the matter encoding it exists, the sound of rain, a mother's voice, the heartbeat, still there in some sense as a physical imprint on matter, even in the darkest, coldest, emptiest era of the universe's existence. Let us talk about something else that will be happening in the dark era, something that will eventually affect the trajectory of Voyager 1 or whatever remnants persist. The universe is expanding, and that expansion is accelerating. We know this from observations of Type Ia supernovae, used as standard candles to measure cosmic distances, and from the detailed structure of the cosmic microwave background. Something, we call it dark energy, but that name is essentially a label on our ignorance, is causing the expansion of space itself to speed up. If dark energy remains constant, as current observations suggest it might, then the universe will continue expanding exponentially in what cosmologists call a de sitter expansion. In this scenario, the universe never reaches a final static state. It expands forever, getting larger and colder and emptier with every passing moment. The average density of matter and energy approaches zero asymptotically, getting closer and closer to nothing, but never quite reaching it. In such a universe, Voyager 1, or its atomic remnants, drifts in an ever-expanding void. The distance between the spacecraft and any other object grows not just because of the spacecraft's own motion through space, but because space itself is stretching between them. Eventually, the separation between Voyager 1 and any other remnant in the universe becomes so large that no physical signal, no photon, no gravitational wave, no quantum interaction of any kind can ever bridge the gap. Everything becomes causally isolated from everything else. In a very real sense, each remnant in the universe becomes its own universe, alone, unreachable, surrounded by an infinite expanding void. I want to pause here because I think we need to acknowledge something directly. This is a genuinely difficult idea to sit with. Not intellectually, though it is that too, but emotionally. The image of Voyager 1 alone in an infinite expanding darkness, the last faint traces of human intention drifting in a universe that has forgotten everything that ever happened in it. That is a heavy image, a lonely one, and I think it is okay to feel that. In fact, I think feeling it is important, because the alternative, treating the deep future of the universe as just a series of numbers and timescales, abstract and disconnected from anything that matters, misses the point entirely. Voyager 1 matters because we made it, because Carl Sagan stayed up late thinking about what music to put on the golden record, because the engineers who built it were thinking about their children and their civilization and their species and what mark they might leave on the cosmos, because the scientists who designed its trajectory were dreaming of a time when humanity would stand at the edge of the solar system and look back. The fact that the universe will eventually expand into cold silence does not retroactively erase any of that. The meaning was real, the intention was real, the reaching was real, and the physics of the universe, the actual, measurable, observable physics, preserves the causal trace of every event that ever happened. The universe remembers even when it seems to have forgotten everything. That is not poetry, that is thermodynamics. If you are still watching, then you are the person I make these videos for. Make sure to subscribe to the channel and give a like. You will be part of a community that explores the cosmos together. Let me tell you about a photograph. On February 14, 1990, Voyager 1 was about 6 billion kilometers from Earth, already far beyond the orbit of Neptune, already deeper into space than any human-made object had ever traveled. The mission team at NASA, led in part by Carl Sagan, made a decision. They turned the spacecraft around. They pointed its camera back toward the inner solar system, toward the sun, toward the planets, toward home, and took a picture. What came back was one of the most important images ever captured by any camera, anywhere ever. In the photograph, against the absolute blackness of deep space, you can see a tiny pale blue dot, barely a pixel, a speck so small it almost disappears into the scattered light of the camera lens itself. That dot, that almost invisible, easy to miss, pale blue dot, is Earth, our planet, every human being who ever lived, every war ever fought, every love story ever written, every city, every ocean, every mountain, every moment of joy and grief and triumph and failure in the entire recorded history of our species, a dot. Carl Sagan wrote about it, and what he wrote has never left me. He said, and I am going to paraphrase here because I want this to feel conversational rather than recited, he said that the photograph reveals something crucial about our situation, that every king and peasant, every saint and sinner, every young couple in love, every mother and father, every inventor and explorer, every teacher and student, all of them lived out their lives on that mote of dust suspended in a sunbeam, that our planet is a very small stage in a vast cosmic arena, that all the rivers of blood spilled by generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot, all of that happened there on us. He said the photograph underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we have ever known. I think about that photograph every time I think about Voyager 1, because the spacecraft that took it, that turned around and looked back at us with one eye before continuing its journey into the dark, is the same spacecraft we have been following through billions of years of cosmic time. And the fact that it captured that image before going silent, before drifting beyond all connection to us, feels like something more than coincidence. It feels like intention, like a goodbye. So here is the question I promised we would sit with. The one that I think everything else in this video has been building toward. Why reach? Why send Voyager 1 into interstellar space? Why put a golden record on it with the sound of rain and a heartbeat, and Chuck Berry? Why build telescopes that look back to the beginning of time? Why dedicate human lives to understanding the death of stars and the expansion of the universe and the decay of protons? Why do any of this when the universe, according to our best physics, ends in cold, dark, empty silence? When every star eventually dies, every planet eventually dissolves, every trace of every civilization is eventually erased by entropy. This is not a rhetorical question, it is a real one. And different people, different scientists, different philosophers, different traditions of human thought answer it differently. I want to share with you the answer that I personally find most compelling, not as a final word, not as settled truth, but as a perspective worth considering. The universe did not have to produce anything that could ask this question. Think about that for a moment. Really think about it. The laws of physics, as far as we can tell, are not specifically arranged to produce consciousness. They are not tuned to generate curiosity or wonder or the capacity to feel grief at the eventual death of the stars. The universe could have been, and for the vast majority of its history has been, a place of pure physical process with no witness. Hydrogen clouds collapsing into stars, stars burning and exploding, heavy elements being scattered through the void, planets forming, all of it happening with the same indifference as a rock rolling down a hill. And then, on at least one small world, orbiting one unremarkable star, in one outer spiral arm of one average galaxy, something happened. Matter became organized in such a way that it could look back at the universe and recognize it, understand it, feel something about it, ask questions about it, name it, love it. That is not nothing. That is arguably the most extraordinary thing that has ever happened in the observable universe. More extraordinary than any supernova, any black hole, any galactic merger, because those are just physics. Consciousness is physics becoming aware of itself, and Voyager 1 that little golden machine, built by conscious beings, carrying the sounds and images of a conscious world, drifting through a universe that does not know it exists, is a physical embodiment of that awareness. It is a piece of the universe that carries, encoded in its very structure, evidence that the cosmos once produced something that noticed it, wondered about it, was moved by it. That, to me, is why we reach, not because reaching will last forever, not because anyone will necessarily receive the message, but because reaching is what consciousness does. It is the universe's way of knowing itself, even briefly, even on the cosmic scale of briefly. Now, I want to bring in something from the science here, because I think it deepens this rather than diminishing it. There is a field of research called astrobiology, the study of the origin, evolution, and potential distribution of life in the universe. It is a young field and a genuinely exciting one because it sits at the intersection of astronomy, chemistry, biology, and planetary science. And one of its central questions is, how common is life in the universe? We do not know the answer. We have exactly one data point, Earth, and one data point is not enough to draw any statistical conclusions. For all we know, life could exist on billions of worlds scattered across the Milky Way, or we could be alone, the only living things in an observable universe containing 2 trillion galaxies. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of technologically advanced civilizations in the Milky Way by multiplying together various factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets that could support life, the fraction on which life actually arises, the fraction where intelligence evolves, and so on. The problem is that for most of these factors, we still have very little data. Different scientists plug in different estimates and get answers ranging from millions of civilizations to fewer than one, meaning we might be unique. The Fermi paradox, named after physicist Enrico Fermi, who allegedly asked the question over lunch in 1950, captures the tension beautifully. If the galaxy is billions of years old, and if technological civilizations are at all common, then some of them should have had enough time to colonize the entire galaxy many times over. So where is everybody? Why do we see no evidence of anyone else out there? There are many proposed answers to the Fermi paradox. Maybe civilizations tend to destroy themselves before they can spread. Maybe interstellar travel is harder than we think. Maybe advanced civilizations deliberately avoid contact. Maybe we are simply not listening in the right way. Maybe the universe is stranger and more surprising than any of our models account for. But one answer, the one that I find both the loneliest and, in a strange way, the most empowering, is this: maybe we are extraordinarily early. Maybe the universe at 13.8 billion years old is still young enough that technological consciousness is vanishingly rare. Maybe we are among the first, the pioneers, the ones who look out into a dark and silent galaxy, not because it is empty of potential, but because that potential has not yet had time to fully flower. If that is true, if we are genuinely among the first conscious questioning, reaching beings in this part of the cosmos, then Voyager 1 takes on a significance that goes beyond anything Carl Sagan or the NASA engineers of the 1970s could have fully articulated. It is not just a message from humanity to whoever might be out there. It is a message from the universe's first generation of witnesses. A record that consciousness existed here, early in the cosmic story, before most of the stars that will ever exist have even formed. Most of the stars that will ever exist in the Milky Way have not yet been born. Most of the planets, most of the potential for life. The universe, in terms of its long-term stellar population, is still in its infancy, and we are here now in that infancy, building golden records and sending them into the dark. That is audacious. That is magnificent. That is profoundly, heartbreakingly human. let me tell you about something that happened in 2023 that I think deserves more attention than it got. Voyager 1, which had already been silent in certain ways due to aging hardware, experienced a serious malfunction. The Flight Data System computer, one of the spacecraft's 3 onboard computers, began sending back garbled, incoherent data. For several months, engineers at NASA's Jet Propulsion Laboratory could not figure out what was wrong. The spacecraft was still receiving commands. It was still transmitting, but the data it was sending back was essentially unreadable, meaningless, and here is the thing that gets me. The signal from Voyager 1 takes over 22 hours to reach Earth, so when engineers sent a command, they waited 22 hours for it to arrive at the spacecraft. Then they waited another 22 hours for the response to travel back. Every single diagnostic test, every attempted fix, every moment of troubleshooting operated on a 44-hour feedback loop. For months, a small team of engineers, many of them young enough that Voyager 1 launched before they were born, worked to diagnose and fix a computer malfunction happening 23 billion kilometers away in a system built with 1970s technology, using programming languages and hardware architectures that are essentially archaeological artifacts, and they fixed it. In April of 2024, after months of painstaking work, the team identified the problem: a single corrupted chip in the Flight Data System memory, affecting about 3% of the computer's total memory. They found a way to work around it, redistributing the affected code to other parts of the memory. And Voyager 1 began sending back clean, readable data again. When I read about that, I sat with it for a long time, because it says something extraordinary about what human beings are capable of when they decide something matters. A team of people, some of them decades younger than the machine they were fixing, reaching across 23 billion kilometers of space with radio waves traveling at the speed of light, coaxing a 47-year-old computer back to life. If that does not make you feel something, some mixture of pride and tenderness and sheer awe at what our species can do when it cares, I genuinely do not know what will. We are made of stardust. You have probably heard that before. It is one of those phrases that gets repeated so often it starts to lose its weight, becomes a bumper sticker or a motivational poster rather than a genuine scientific statement. But I want you to hear it again right now with fresh ears. Every atom of carbon in your body was forged in the nuclear furnace of a star that died before the Earth existed. The iron in your blood was created in a supernova explosion, a stellar death so violent it briefly outshone an entire galaxy. The oxygen you are breathing was synthesized in the cores of massive stars over billions of years and scattered through the galaxy by stellar winds and explosions. The calcium in your bones, the phosphorus in your DNA, the sulfur in your proteins, all of it, every atom of it, traces its origin to the interior of a star. You are not just living in the universe, you are made of it. You are a temporary, extraordinarily complex, self-aware rearrangement of the saintomat that has been cycling through stars and clouds and planets for 13.8 billion years, and so is Voyager 1. The aluminum in its frame, the copper in its golden record, the gold in its plating, all of it came from the same source as you, forged in stellar furnaces, scattered through space, gathered by gravity into a solar system, refined by geological processes, shaped by human hands, launched into the void. When Voyager 1 carries its golden record through the interstellar medium, when it drifts past dying stars and through ancient molecular clouds, it is, in a real sense, stardust carrying a message back to the stars. Matter that was born in the cosmos, briefly organized by consciousness into something meaningful, released back into the cosmos it came from. There is a poetry in that which I find more moving than anything I have ever encountered in actual poetry, not because it is metaphorical, but because it is literal. Here is something else worth sitting with. In every direction you look in the night sky, you are looking back in time. The light from the moon left about 1.3 seconds ago. The light from the sun left 8 minutes ago. The light from the nearest star, Proxima Centauri, left 4.2 years ago. The light from the Andromeda galaxy left 2.5 million years ago, when our ancestors were stone tool, using hominids on the African savanna. When you look at the night sky, you are not seeing the universe as it is. You are seeing it as it was, a layered archive of the past, each distance corresponding to a different moment in history. The universe, as we perceive it, is a fossil record written in light. Voyager 1 is the opposite of that. It is not light traveling toward us from the past. It is matter, physical, tangible stuff, traveling away from us into the future. While starlight brings us news of the past, Voyager 1 carries our message into what comes next, into times and distances we cannot see or measure, into a future so remote it makes our entire recorded history feel like a single afternoon. In that sense, Voyager 1 is the furthest forward-pointing thing our civilization has ever produced, a physical ambassador to the future of the cosmos. I want to address one more thing before we move into the final chapters of this journey, and it is something I think about a lot personally. It is the question of legacy. We live in a world that is at the moment quite good at making us feel small in a discouraging way rather than a liberating one. Social media reduces identity to metrics. News cycles shrink our attention to hours. The scale of global problems can make individual human lives feel irrelevant, like single grains of sand on a beach that stretches to every horizon. But Voyager 1 suggests a different framing. It suggests that a single act of intention, a single decision to reach, to build, to encode something meaningful and send it into the unknown, can have consequences that outlast not just your lifetime, but your civilization, your planet, your star, your galaxy. That the things we make with genuine care and genuine purpose are not erased by time, but carried by it, transformed by it, yes, worn by it, certainly, but not meaningless. Your life is not a pale blue dot. It is a source of light, small yes, brief yes, but real, and in a universe that, as far as we can tell, does not have to produce light at all. Real matters enormously. Now let's come back to the physical journey. We are going to talk about the very last destination, the final place in the most literal sense that Voyager 1 will reach. Not metaphorically, not philosophically, physically. We are going to follow the spacecraft all the way to its ultimate resting place, based on everything physics currently tells us. And I will warn you now, the answer is not what most people expect. It is stranger, and in its own way, it is more beautiful. We started this journey with a question, a specific, concrete, almost deceptively simple question. Where does Voyager 1 end up? What is the final place it will reach before it dies? And after? We have spent 7 parts building the context needed to answer that properly. We have followed the spacecraft from its launch pad in 1977 through the solar system, past Jupiter and Saturn, through the heliopause, into interstellar space. We have traced its path through the Oort Cloud, past neighboring stars, through the galactic disk, through the Milky Way and Andromeda merger, through the death of the last stars, through the evaporation of the last black holes, and into the cold silence of the dark era. Now it is time to answer the question directly, as honestly and as completely as current physics allows. And to do that, we need to split the answer in two, because there are 2 different senses in which Voyager 1 has a final destination. There is the physical final place, the last location in space where its matter will reside in a recognizable form, and there is the deeper final place, the endpoint of everything that Voyager 1 represents. In the grand arc of cosmic time, both answers are extraordinary. Let us take them one at a time. First, the physical. After the Milky Way and Andromeda merge into Milky, roughly 4.5 billion years from now, The combined galactic structure will go through a long, turbulent period of reorganization. Tidal streams of stars will arc across enormous distances. Some stars will be flung outward into intergalactic space. Others will spiral inward toward the growing supermassive black hole at the center of the merged galaxy. The spiral arms that currently give both galaxies their elegant structure will be disrupted and eventually smoothed out as the merger progresses, leaving behind a large, roughly elliptical galaxy, less dramatic looking than either of its predecessors, but far more massive. During this merger, Voyager 1, already thousands of light-years from any recognizable remnant of our solar system, will be subject to the large-scale gravitational tides of the collision. Its trajectory will be nudged, perhaps significantly. The outcome depends on details of the gravitational dynamics that are frankly impossible to calculate precisely from where we stand today. The merger is chaotic at the stellar scale, and small perturbations compound into large trajectory changes over billions of years, but we can sketch the broad possibilities. Possibility 1. Voyager 1 remains loosely gravitationally bound to the Milky remnant. It orbits the merged galactic structure at large radius, dipping in and out of the outer reaches of the galaxy over billions of years, gradually having its orbit modified by gravitational interactions with passing stellar remnants. Over the very long term, timescales of 10 to the 19 to 10 to the 20 years, even this loose association ends as gravitational evaporation slowly strips the outer stellar population from the galaxy. Voyager 1 eventually drifts free, ejected into the intergalactic void by a chance gravitational encounter. Possibility 2. Voyager 1 is ejected from the galaxy during the merger itself, flung outward by the gravitational chaos of the collision into the vast dark space between galactic remnants. In this scenario, it becomes a true intergalactic nomad far sooner, drifting not just between stars but between entire galactic structures in a void so empty that the average particle density is roughly 1 atom per cubic meter, thousands of times emptier than the already sparse interstellar medium. Possibility 3, the one that I find most cosmically dramatic. Voyager 1, through a sequence of unlikely but non-impossible gravitational encounters over billions of years, finds its trajectory gradually bent inward toward the galactic center, closer and closer over enormous timescales to the supermassive black hole that anchors the Milky remnant. And eventually, not in a dramatic in-spiral, not quickly, but through the slow accumulated effect of gravitational dynamics, it crosses the point of no return, the event horizon. Let us think carefully about what that would mean. Because black holes are one of those topics where popular culture has given us a set of dramatic images, crushing, tearing, spaghettification, that, while not entirely wrong, miss a lot of the genuine strangeness of what general relativity actually predicts. The supermassive black hole at the center of Milky, by the time we are talking about, billions upon billions of years after the merger, will have grown significantly from its current mass. It could be hundreds of millions or even billions of solar masses, having consumed gas clouds, stellar remnants, and anything else that strayed too close over cosmic time. A black hole of that mass has an event horizon, the boundary beyond which escape is impossible, with a radius of billions of kilometers. And here is the thing that surprises most people about a supermassive black hole's event horizon. It is not a violent place, not at the horizon itself. The tidal forces, the difference in gravitational pull between one side of an object and the other, at the event horizon of a sufficiently massive black hole are actually quite gentle. Gentle enough that a spacecraft the size of Voyager 1 would cross the event horizon without being immediately torn apart. There is no wall, no visible boundary, no dramatic change in the local environment at the moment of crossing. General relativity predicts that an observer falling into a large black hole would experience the crossing of the event horizon as completely unremarkable. The local physics feels normal. The laws of nature do not suddenly change. Nothing explodes or tears or shifts dramatically. You simply cross a line that you cannot come back from. Of course, Voyager 1 would not experience any of this consciously. It is a machine, long dead, drifting through the dark, but the physics is the same. If the spacecraft approaches the event horizon of a supermassive black hole and crosses it, there is no dramatic final moment. Just a boundary, invisible and unmarked, beyond which the future points only inward. From outside the black hole, from any hypothetical vantage point in the universe beyond, something extraordinary happens, at least in principle. Due to the extreme time dilation near the event horizon predicted by general relativity, an outside observer would never actually see Voyager 1 cross the horizon. Time as experienced by the infalling object runs slower and slower relative to time in the outside universe as it approaches the horizon. The spacecraft would appear to slow down, its signals becoming increasingly redshifted, stretched to longer and longer wavelengths until it appears to freeze at the horizon, its image growing dimmer and dimmer, redshifting toward infrared and radio wavelengths, effectively disappearing from view, not crossing the horizon in any finite amount of outside time, just fading. But from Voyager 1's perspective, from the frame of reference of the infalling object, the crossing happens in finite time, and beyond the horizon, the story continues for a while, inside the black hole. Beyond the event horizon, the physics of general relativity predicts something that is simultaneously precise and deeply strange. The singularity, the point at the center of a black hole where the known laws of physics break down, is not a place in the usual sense. It is better described as a moment in time, a future that every infalling trajectory inevitably points toward once the horizon has been crossed. In the Schwarzschild solution, the mathematical description of a non-rotating black hole. Once inside the event horizon, the spatial dimension pointing toward the center and the time dimension effectively swap roles. Falling toward the singularity is not like falling toward a point in space. It is like falling toward a moment in time, a moment you cannot avoid, cannot orbit around, cannot escape. Because you cannot travel backward in time any more than you can travel backward in space outside the black hole, how long does it take to reach the singularity after crossing the horizon? For a supermassive black hole, one of billions of solar masses, the answer could be hours or even days of proper time for the infalling object, but it is finite, the journey ends, and at the singularity, or rather, at whatever actually exists where our current equations predict a singularity, since most physicists believe the true answer requires a quantum theory of gravity that we do not yet possess. Something happens to the matter that crossed the horizon. We do not know what. Our physics genuinely breaks down at that point. It is not that we have the wrong answer. It is that we do not yet have the framework to even ask the question properly. This is one of the great open frontiers of theoretical physics. The interior of a black hole, and specifically the nature of the singularity, is a place where general relativity and quantum mechanics both fail to give consistent answers, and where a true theory of quantum gravity is desperately needed. String theory, loop quantum gravity, and other approaches all have something to say about this, but none of them have yet produced experimentally testable predictions that would tell us which description is closest to reality. So, in a profound sense, the final destination of Voyager 1, if it ends its journey inside a black hole, is a place that physics currently cannot describe, a region beyond the reach of our best theories, a genuine frontier. And I find something wonderful in that. The spacecraft that pushed past the known edges of the solar system, that crossed the heliopause into uncharted interstellar space, that traveled further from its origin than anything our civilization has ever built, may ultimately end its journey at the boundary of what physics itself can currently describe. At the edge of the known, one final time. But wait, we said earlier that black holes eventually evaporate through Hawking radiation. So what happens to everything that fell in? This is the black hole information paradox, one of the most hotly debated questions in theoretical physics for the last half-century. When matter falls into a black hole and the black hole eventually evaporates, what happens to the information encoded in that matter? The laws of quantum mechanics say that information cannot be destroyed, that the quantum state of a system must be preserved, even if its form changes dramatically. But Hawking's original calculation suggested that the radiation emitted during evaporation is purely thermal, random, carrying no information about what fell in. If that were true, information would be genuinely lost, and that would violate a fundamental principle of quantum mechanics, setting general relativity and quantum theory in direct, irreconcilable conflict. Most physicists today believe that information is not lost, that it is somehow encoded in the Hawking radiation, scrambled beyond any practical recovery, but physically present in the correlations between outgoing particles. Stephen Hawking himself eventually came around to this view before his death in 2018, conceding that information is probably preserved. But the exact mechanism, how information escapes from inside a black hole and becomes encoded in the radiation, is still not fully understood. It is an active area of research involving some of the sharpest minds in theoretical physics. What this means for Voyager 1, if it falls into a black hole, is profound. The information encoded in the spacecraft, including the information encoded in the Golden Record, would not be destroyed when the black hole evaporates. It would be released back into the universe, scrambled almost infinitely beyond any hope of reconstruction, carried in the quantum correlations of Hawking radiation photons spreading across the cosmos, the sound of rain, the heartbeat, the music, transformed into thermal radiation spread across the universe, unreadable, unrecoverable, but not gone, not truly gone, just returned to the cosmos in the most thoroughly mixed form imaginable, the universe keeping its records. Now, let us address the scenario where Voyager 1 is not swallowed by a black hole, where it is instead ejected into the intergalactic void, drifting free of any galactic structure, tumbling through the enormous emptiness between galactic remnants in the degenerate and dark eras. In this scenario, the final physical resting place of Voyager 1 is nothing. Not nothing dramatically, just nothing quietly. The spacecraft drifts through a universe that becomes progressively more homogeneous, more dilute, more featureless with each passing cosmic era. If proton decay occurs, the spacecraft dissolves over timescales of 10 to the 34th to 10 to the 40th years, its atoms converting to photons and leptons that spread outward at the speed of light, diluted by an ever-expanding universe into a signal indistinguishable from background noise. If proton decay does not occur, the atoms persist essentially forever, cold, inert, their quantum states frozen as close to ground state as physics allows, drifting through a universe that has nothing left to offer them in terms of interaction or change. The spacecraft persists as a physical object, increasingly unrecognizable, for time scales that essentially have no upper bound. In both cases, the answer to the question of the final physical resting place is the same, in essence, the universe itself, not a specific location, not a named destination, just the cosmos, the vast, expanding, darkening cosmos from which every atom of Voyager 1 was originally borrowed. It goes back, that is where it ends up. It goes back to where it came from. And there is the other answer I promised, the deeper one, the final place that Voyager 1 reaches not in physical space, but in meaning. Voyager 1's ultimate destination, the place it has been heading all along, without anyone necessarily designing it that way, is the permanent record of the universe itself. Here is what I mean by that. Every event that happens in the universe leaves a causal trace. A photon emitted by a star 4 billion years ago is still traveling through space, carrying information about the star that released it. A gravitational wave generated by two black holes merging 1 billion light-years away rippled outward in all directions and will continue traveling through the fabric of space-time essentially forever. A cosmic ray particle accelerated by a supernova explosion hundreds of millions of years ago is still crossing the galaxy, hitting Voyager 1 at this very moment. The universe is not a place where things happen and then are forgotten. It is a place where every event is physically encoded in the state of everything that came after it. The present state of the universe, the arrangement of every particle, the trajectory of every photon, the curvature of space-time at every point is, in principle, a record of everything that has ever happened. Not a readable record by any technology we can currently conceive of, but a physical one. Voyager 1 is part of that record, its launch, its encounters with Jupiter and Saturn, the pale blue dot photograph, the golden record, the signal going silent, the drift through interstellar space, the crossing of the heliopause. All of it is encoded causally in the state of the universe moving forward from each of those moments. It cannot be erased, not by entropy, not by expansion, not by the death of stars. It is woven into the causal fabric of the cosmos. The final place Voyager 1 reaches is not a location in space. It is a location in history, in the permanent, indelible, physical history of the universe. It gets there the moment it launches, and it never leaves. There is a concept in physics called the block universe, also called eternalism in philosophy. The idea, which follows from the geometry of space-time in Einstein's special and general relativity, is that past, present and future are all equally real, all existing simultaneously in the four-dimensional structure of space-time. The distinction between past and future is, in this view, a feature of our subjective experience, of the direction in which our consciousness moves through time, rather than an objective feature of the universe itself. If the block universe interpretation is correct, and many physicists find it the most natural reading of relativistic physics, then September 5, 1977, the day Voyager 1 launched, is not gone. It is just a different location in space-time. The launch is still happening in the same sense that a city 1,000 kilometers away still exists even though you cannot see it. The moment Carl Sagan stood in a room and listened to the golden record for the last time before it was sealed and mounted on the spacecraft, that moment exists. Permanently, unchangeably, written into the geometry of the universe itself. And in that sense, Voyager 1 never goes anywhere we cannot follow. It is always, simultaneously, sitting on a launch pad in Cape Canaveral and flying past Jupiter and crossing the heliopause and drifting silent and frozen through the interstellar dark and dissolving into photons in the dark era and encoded in Hawking radiation spreading outward from an evaporating black hole. All of it at once, forever, in the four-dimensional block of space-time that is the universe. The final place Voyager 1 reaches is everywhere it has ever been, all at once, permanently. That is not poetry. That is geometry. There is a building in Pasadena, California, that does not look like much from the outside. A cluster of low, functional structures spread across a campus nestled against the foothills of the San Gabriel Mountains. No dramatic architecture, no gleaming futuristic facade. Just buildings full of computers and antennas and people who spend their working lives communicating with machines that are no longer anywhere near this world. This is the Jet Propulsion Laboratory, JPL, and for nearly 50 years, it has been the home of the Voyager mission, the place where every command sent to Voyager 1 originates and where every signal coming back from the spacecraft, traveling at the speed of light for over 22 hours before it arrives, is received, decoded, and turned into science. I want to spend some time here, in the present, with the people. Because we have spent most of this video thinking at the scale of billions of years, and I think it is important to come back down to the human scale, to the offices and computer screens and coffee cups and the particular kind of quiet that descends over a room when a signal arrives from 23 billion kilometers away. The people currently working on the Voyager mission are, in many cases, young enough that the spacecraft launched before they were born. Think about what that means for a moment. Voyager 1 left the Earth in 1977. Anyone who was, say, 25 years old and working on the mission at that time is now in their early 70s. The original team, the people who calculated the trajectories, who designed the instruments, who fought to get the golden record approved and funded and built, most of them are retired or no longer with us. What remains is a team of engineers and scientists who inherited the mission, who learned the quirks of 1970s technology, not from direct experience, but from documentation and from the mentorship of the previous generation, who had to teach themselves obsolete programming languages and hardware architectures specifically to keep the spacecraft communicating, who love a machine they never watched launch, keeping faith with a journey that was already decades old when they joined it. There is a particular kind of dedication in that. It is not the excitement of launching something new. It is the quieter, perhaps more profound commitment of maintaining something ancient, of refusing to let the signal go silent one moment before it has to. Let us talk about what the mission looks like right now. In 2024 and into 2025, Voyager 1 is currently more than 23 billion kilometers from the Sun. It is traveling in the direction of the constellation Ophiuchus at roughly 17 kilometers per second. The one-way signal travel time, the time it takes for a radio signal traveling at the speed of light to reach the spacecraft, is over 22 hours. The round trip for a command sent from Earth and a response received back takes over 44 hours. The spacecraft is powered, as we discussed in Part 1, by 3 radioisotope thermoelectric generators. Their output has declined to somewhere around 70 watts. To keep the most critical systems alive, specifically the communication system and the most valuable remaining science instruments, the mission team has been making agonizing decisions about what to turn off. Heaters that keep certain components from freezing have been switched off, a risk because some systems were never designed to operate at the temperatures of deep space without them. Science instruments have been powered down one by one over the years, reducing the data returned from the spacecraft, but extending the mission life of the systems that remain. Every watt counts. Every decision involves a trade-off between immediate data return and long-term mission survival. The current science instruments still operating on Voyager 1 include plasma wave detectors and cosmic ray detectors, instruments that are measuring the properties of the interstellar medium through which the spacecraft is currently passing. Every day, these instruments send back data that is genuinely irreplaceable, because there is no other spacecraft anywhere near Voyager 1. No other human-made object has ever been this far from the Sun. The data coming back from Voyager 1 right now, today, as you watch this video, is the only direct in situ measurement of conditions in the local interstellar medium that we have. It cannot be obtained by telescope. It cannot be modeled from Earth with sufficient precision. It can only be measured by being there, and only one thing has ever been there. This little spacecraft, built in the 1970s, running on 70 watts, talking to us across 22 hours of light travel distance. Now, I mentioned the 2023 malfunction a while ago. the corrupted chip in the flight data system that caused months of garbled transmissions and required an extraordinary diagnostic effort by the engineering team. I want to go a little deeper into that story because I think it illustrates something important about the nature of this mission and the people running it. When Voyager 1 began sending back the garbled data in late 2023, the first challenge was simply figuring out what was wrong. The spacecraft has 3 computers: the flight data system, which collects data from the science instruments and formats it for transmission; the command control system, which processes commands sent from Earth and directs spacecraft operations; and the attitude control system, which keeps the spacecraft oriented correctly so its antenna points toward Earth. The garbled data was coming from the flight data system, but the other 2 computers appeared to be functioning normally. The spacecraft was still receiving and executing commands, still keeping its antenna pointed in the right direction. Something was wrong with specifically how data was being packaged and sent, but not with the spacecraft's ability to communicate at all. The diagnostic process was painstaking. Engineers sent commands asking the spacecraft to return information about its own systems, one piece at a time, trying to map out what was working and what was not. Every test took 44 hours to complete. Every hypothesis had to wait nearly 2 days to be confirmed or refuted. What they eventually discovered was that a single chip in the flight data system memory, specifically a chip responsible for a section of the memory that stores some of the code the system uses to package data, had been corrupted. The leading hypothesis is that this was caused by radiation damage. After 47 years of exposure to cosmic rays and high-energy particles, a single chip had finally been hit in exactly the wrong way, flipping bits in the stored code and causing the system to malfunction. The fix they devised was elegant in its simplicity and extraordinary in its execution. They could not repair the chip. That was physically impossible from Earth. So instead, they moved the affected code to a different part of the memory that was still functional. But here is the challenge. The code was too large to fit in any single available section of the remaining memory. They had to divide it into pieces and store each piece in a different location, then modify the code itself to ensure all the pieces communicated correctly with each other. They were essentially doing a live, remote surgery on the memory architecture of a 47-year-old computer that was 23 billion kilometers away, in a programming language that most computer science programs no longer teach, with a 44-hour feedback loop on every step. And they did it. Piece by piece, over several weeks, they uploaded the modified code sections. In April of 2024, Voyager 1 began returning clean, usable science data for the first time in months. When I read the official announcement from JPL about that recovery, I noticed something in the language the engineers used. They did not sound triumphant, exactly. They sounded relieved, quietly, deeply relieved, like people who had been holding their breath for months and had finally been allowed to exhale because they know what is coming. They know the power is declining. They know the decisions are only going to get harder. They know that at some point, probably in the next year or 2 from when you are watching this, there will be a final command sent, a final response received, a final moment when the signal from Voyager 1 is present and then is not, and they are the ones who will be there for it. I want to talk about what that means. The end of the signal. The moment the mission officially concludes, when Voyager 1's power output falls below the threshold needed to operate even its most basic communication system, the spacecraft will stop transmitting. It will not announce its own death. There will be no final message, no ceremonial last words. The signal will simply stop arriving. The antenna dishes of the deep space network, the global array of giant radio telescopes, that NASA uses to communicate with spacecraft across the solar system and beyond will keep listening, pointed at the right part of the sky, tuned to the right frequency, waiting, and nothing will come. At some point, the mission team will make the formal determination that the spacecraft has lost the ability to transmit, and the Voyager 1 mission, as an active scientific endeavor, will be over. The Deep Space Network, which currently allocates time to communicate with Voyager 1 on a regular schedule, will redirect those resources to other missions. The team that has been maintaining the spacecraft, troubleshooting its problems, nursing its failing systems, will move on. Some to other missions, some to retirement. Some will carry the memory of it for the rest of their lives. And somewhere, 23 billion kilometers away, the spacecraft itself will continue. Silent now, dark, still moving at 17 kilometers per second, still carrying its golden record, still pointed roughly in the direction it has always been pointed. Because the attitude control system will eventually lose power too, and the spacecraft will slowly tumble, no longer maintaining its precise antenna orientation, drifting into whatever rotation the residual torques of space eventually impart to it. It will tumble silently through the interstellar dark, alone in a way that no human-made object has ever been alone before. I think it is worth pausing to appreciate the Deep Space Network, because it is one of the most extraordinary pieces of infrastructure our civilization has ever built, and most people have never heard of it. The Deep Space Network consists of 3 main antenna complexes positioned roughly 120 degrees apart in longitude around the Earth, one near Goldstone, California, in the Mojave Desert, one near Madrid, Spain, and one near Canberra, Australia. The 3 locations are chosen so that as the Earth rotates, at least one complex always has line of sight to any spacecraft in the solar system or beyond. The largest antennas in the network have dishes 70 meters in diameter, roughly the length of 2.5 Olympic swimming pools across. They are so sensitive that they can detect signals with a power level of less than 10 to the negative 26 watts, a number so small it is essentially meaningless to describe in everyday terms. The signal arriving from Voyager 1 right now has less power than the light from a single firefly at a distance of several thousand kilometers. The fact that we can hear it at all is a testament to the engineering of both the spacecraft and the network, and the fact that we are still listening, still allocating time on these enormous, expensive antennas to receive data from a spacecraft launched half a century ago, says something about the value the scientific community places on the irreplaceable data Voyager 1 continues to provide. There are currently many spacecraft competing for time on the Deep Space Network, Mars missions, the James Webb Space Telescope's data relay, various planetary probes, and yet Voyager 1 gets its time. The science it returns, fragile, faint, traveling for over 22 hours through space before arriving, is still considered worth the resources. Still, let us talk about what that science actually tells us. Because in the midst of all the philosophy and the deep time thinking we have been doing, I do not want to lose sight of the fact that Voyager 1 is still, right now, doing science, still contributing to our understanding of the universe. The plasma wave instrument on Voyager 1 has been detecting and measuring electron density in the interstellar medium, and the results have been surprising. Scientists expected the interstellar medium to be relatively quiescent, a thin, quiet medium with occasional perturbations from distant stellar events. What they have found instead is that the interstellar medium has a persistent low-level hum, a kind of background vibration in the plasma that seems to exist independent of specific events. This was reported in a 2021 paper in the journal Nature Astronomy based on data from Voyager 1. The spacecraft detected what researchers described as a faint, persistent plasma wave emission in the frequency range of 2 to 3 kHz. This signal appears to be continuous, not associated with any specific event, and seems to represent a baseline level of activity in the interstellar medium that had not been previously anticipated. What causes it? The leading hypothesis involves photoionization, the process by which ultraviolet light from distant stars ionizes hydrogen in the interstellar medium, creating a low-level, persistent electron density. But the details are still being worked out, and the data from Voyager 1, the only spacecraft actually in the interstellar medium, is essential to understanding it. Think about that. Right now, Voyager 1 is telling us things about the universe that we could not learn any other way. Not from telescopes on the ground, not from space observatories in Earth orbit, not from any other spacecraft in the solar system, only from this one specific machine, in this one specific place, transmitting its faint signal home for as long as it possibly can. There is another layer to this story that I think deserves attention. And that is the question of what comes next. Because even as Voyager 1 approaches the end of its transmission life, the spirit of what it represents, the drive to send something further, to reach deeper, to know more, is very much alive. Several mission concepts have been proposed over the years for a dedicated interstellar precursor mission, a spacecraft specifically designed from the outset to enter interstellar space and return data from there, rather than doing so as a secondary achievement after a planetary science mission like Voyager. These concepts have names like the Interstellar Probe, a study conducted for NASA that proposed launching a spacecraft to reach a distance of 1,000 astronomical units from the Sun within 50 years of launch, using a solar sail or other advanced propulsion concept. The scientific goals of such a mission would include studying the heliosphere and its interaction with the interstellar medium in far more detail than Voyager could, imaging the solar system from outside, seeing our own star system as a distant object the way other civilizations might see it, and potentially characterizing the local interstellar medium in ways that would inform our understanding of star formation, galactic structure, and cosmic ray propagation. As of my knowledge cutoff, no such mission has been formally approved or funded, but the scientific case for it is strong, and the Voyager missions have demonstrated both that the journey is physically possible and that the scientific return is extraordinary. Whatever comes next in interstellar exploration will build directly on everything Voyager 1 has taught us, because that is how science works. Each generation of instruments, each mission, each discovery extends the reach of the one before it. Voyager 1 stands on the shoulders of every spacecraft and telescope that preceded it, and whatever comes next will stand on Voyager 1's shoulders. The reach is cumulative, the knowledge is inherited, the journey is continuous, even when individual missions end. I want to take a moment to talk about the Golden Record one more time. Because we have mentioned it throughout this video, but I want to give it a proper final moment before we wrap up this penultimate part. The Golden Record was not, strictly speaking, a science instrument. It had no detectors, it sent back no data. It contributed nothing to Voyager 1's scientific mission in any direct sense. It was included because Carl Sagan and his colleagues argued, successfully, that a spacecraft leaving the solar system should carry something of human culture, something that said, we were here, we thought, we felt, we made things, we loved. The selection process was extraordinary. Sagan assembled a committee that included scientists, musicians, anthropologists, and artists. They had an almost impossibly short amount of time, weeks, not months, to choose the sounds and images that would represent Earth to the universe. Every choice involved debate. Every choice involved the recognition that whatever they selected was inevitably partial, inevitably limited, inevitably a reflection of the particular perspectives and cultural moments of the people doing the selecting. Andromeda, who was the creative director of the Golden Record project and who later became Carl Sagan's wife and life partner, recorded her own brainwaves for the record. While her brain was being scanned, she meditated on the history of Earth, on the beauty of the planet, on the idea of love. Her neural activity, the actual electrical patterns of a thinking, feeling human brain, was converted to audio and encoded on the record. There is a human brain on the Golden Record, dreaming of love, hurtling through the interstellar dark. She later said that she and Sagan fell in love during the creation of the record, that the intensity of what they were doing together, the weight of it, the significance of trying to distill humanity into a single object, created a connection between them that led to one of the great scientific and creative partnerships of the 20th century. Love made it onto the Golden Record in ways its creators did not fully realize at the time, not just in the music and the greetings and the images. In the very process of making it, Voyager 1 is going to fall silent, probably soon, and when it does, the last direct physical link between us and the most distant human-made object in history will be severed. We will no longer know from moment to moment where exactly it is or what it is experiencing. It will drift out of our awareness the way a ship disappears below the horizon, not destroyed, not ended, just beyond the reach of our senses. How do you hold that? What do you do with the fact that something made by human hands, carrying the sounds of human life, will continue existing in some form for billions of years after every human being alive today, after every human being who will ever live is gone? I think the answer, or at least part of it, is this: you hold it with gratitude. Gratitude that we live in a time when such a thing was possible. Gratitude that there were people brilliant and bold and romantic enough to build it. Gratitude that the universe is old enough and large enough and strange enough to make such a journey possible. And gratitude that you, sitting here right now, are one of the conscious beings in this cosmos who got to know the story. Not everyone gets to know the story. Most of the universe does not get to know any stories at all. The fact that you do, that you are a thinking, feeling, story-knowing piece of this cosmos is the most extraordinary thing about you. Do not take it lightly. Every journey has a last step, not a dramatic one. Usually, not a moment with trumpets and crowds and the kind of clarity that makes for good cinema. Most last steps are quiet, ordinary-looking, indistinguishable from the 1,000 steps that came before them, except in retrospect. You only know it was the last one after you have already taken it. Voyager 1's last step will be like that. A signal arriving at a dish antenna in California or Spain or Australia. A number appearing on a screen somewhere in Pasadena. An engineer looking up from a workstation and then looking back down and then looking up again. A conversation, a phone call, a room going quiet. And then the listening. The patient, faithful, ultimately unanswered listening that will continue for a while after, just in case, just to be sure. And then the acknowledgement, formal and final, that the most distant journey in human history has entered its silent phase, that the machine is still out there, will always be out there, but that we can no longer hear it. That moment has not happened yet. As of now, as of today, the signal is still arriving, faint as a whisper at the bottom of a well, but arriving. Savor that. It matters. Let us do something we have not done yet in this video. Let us stand still for a moment and look at the full arc of what we have covered. Because I think when you see it all at once, something happens. Something clicks into place that does not click when you are moving through it piece by piece. We started with a spacecraft, a machine the size of a small car, built in the 1970s, launched in September of 1977 on a trajectory calculated to take advantage of a rare planetary alignment that will not recur for another 175 years. a machine carrying a golden record, the compressed essence of human culture, encoded in gold, attached to its side like a name tag on the most extraordinary traveler in history. We watched it cross the solar system, fly past Jupiter with its storms and its moons and its crushing magnetic field, fly past Saturn through the rings and the haze and the moon Titan with its thick orange atmosphere, and then outward, past the orbit of Uranus, past Neptune, into the heliosphere's outer reaches, where the solar wind begins to falter and the interstellar medium pushes back. We watched it cross the heliopause in 2012, the boundary that separates our sun's domain from the true interstellar space beyond, the first human-made object to make that crossing, to enter, physically, the space between the stars. We followed it through the interstellar medium, the thin, ancient gas and dust between stellar systems. We talked about the Oort Cloud, that it has not yet reached and will take tens of thousands of years to pass through. We talked about the star it will make its closest approach to in roughly 40,000 years, a red dwarf called Gliese 979, passing within about 1.6 light-years without stopping, without slowing, a silent visitor in the night. We followed its path through cosmic time, through the merger of the Milky Way and Andromeda, through the death of the last stars, through the Degenerate Era, when the only light comes from cooling stellar remnants, through the evaporation of the last black holes via Hawking radiation, into the Dark Era, a universe so cold and empty and featureless that time itself becomes almost meaningless. We asked why we reach. We talked about consciousness as the universe knowing itself. We talked about the pale blue dot photograph and what it means to see your entire world reduced to a single pixel in the darkness. We talked about love being encoded in a golden record. We talked about human brains dreaming of connection, their electrical patterns pressed into gold and sent into the void. We talked about the final physical resting place, the dissolution of atoms, the release of information into Hawking radiation, the return of stardust to the cosmos, and we talked about the deeper final place, the permanent indelible causal record of the universe itself, where every event that has ever happened is encoded in the physical state of everything that came after it, where Voyager 1's launch is not a memory but a fact of space-time geometry, permanent, unchangeable, real. And now we are here, at the end, at the place where the script wraps up and the video fades and you sit with whatever this has stirred in you. Let me try to make that worthwhile. There is a concept that physicists and philosophers sometimes call the overview effect at cosmic scale. The overview effect, in its original meaning, refers to the cognitive shift reported by astronauts when they see the Earth from space for the first time, the sudden, visceral, often overwhelming realization that national borders are invisible from orbit, that the planet is a single, fragile, achingly beautiful system, that the things that divide us are human inventions, and the thing that unites us, this living world spinning in space, is real. The overview effect has been described by astronauts from dozens of countries, and it almost always produces the same response, a kind of grief and tenderness and fierce protectiveness all at once. What we have been doing in this video, I would argue, is attempting a version of that effect at a scale several orders of magnitude larger, not the scale of low Earth orbit, not even the scale of the solar system, the scale of cosmic time, the scale of billions of years, galactic mergers, the death of stars, the long freeze of the Dark Era. And at that scale, something happens to the things we usually consider important, the things that consume our days, the anxieties, the grievances, the competitions, the endless noise of modern life. They do not disappear, but they shift, they find their proper proportion, they become what they actually are, small, temporary, local disturbances in the life of a planet that is, itself, a small, temporary, local feature of a cosmos that has been unfolding for 13.8 billion years, and will continue unfolding for trillions more. That is not meant to make you feel insignificant, quite the opposite. Because the alternative to feeling small in a discouraging way is to feel small in a liberating way, to recognize that the smallness of your problems does not diminish the largeness of your life, that you are, right now, one of the vanishingly rare arrangements of matter in this universe that gets to experience it, that can be moved by it, that can send a golden record into it and mean something by that gesture. You are not a pale blue dot. You are a perspective on a pale blue dot. And that is something the pale blue dot itself cannot be. I want to talk about legacy one more time, because I think it is the note this video needs to end on. We live in a culture that is, at the moment, quite confused about what legacy means. Social media has given us the illusion that legacy is about reach, about how many people see your face, know your name, engage with your content, that the measure of a life is its digital footprint. That significance requires scale. Voyager 1 suggests something different. The people who designed the trajectory that carried Voyager 1 past 4 planets in a single mission, the people who spent years calculating and recalculating orbital mechanics to make the grand tour possible, most of them are not famous. You could not name them, their faces are not on anything. The culture did not make them celebrities, but the thing they built is going to outlast every celebrity, every empire, every institution, every star in the sky. Their work, their careful, precise, deeply human work, is encoded in the path of an object that will drift through the cosmos for longer than we have language to describe. That is legacy, not reach, not recognition, contribution. The quiet, faithful, skillful act of making something real and good and true and sending it forward into a world or a universe that will be shaped, however slightly, by the fact that you did it. Carl Sagan died in December of 1996 at the age of 62. He did not live to see Voyager 1 cross the heliopause. He did not see the pale blue dot photograph become one of the most reproduced images in history. He did not see the James Webb Space Telescope image the first galaxies, or the Event Horizon Telescope photograph a black hole, or the detection of gravitational waves that confirmed yet another prediction of general relativity. He did not see any of it, but he contributed to all of it. His books, his television series, his advocacy for science and reason and wonder, his insistence that the cosmos deserves our full emotional and intellectual attention, all of that shaped the culture of science in ways that rippled forward through every discovery made after his death. His reach extends beyond his lifetime in every direction, and the golden record, this strange, beautiful, impractical, magnificent object he fought to put on a spacecraft heading out of the solar system that will outlast not just Carl Sagan but the sun itself. It will be out there, carrying his fingerprints in the most literal sense, long after every trace of his name has been erased from whatever comes after humanity. That is what it looks like when a life means something at the scale of the cosmos. Now, the final question, the one the title of this video has been pointing toward from the very beginning. What is the final place Voyager 1 will reach before it dies? And I want to give you two answers now, because I think they are both true, and I think they need to be held together. The first answer is physical. Voyager 1 will drift through interstellar space for millions of years, passing near stars it will never visit, crossing the vast emptiness of the galactic disk, surviving the death of our sun and the cooling of the solar system's remnants. Eventually, through processes of gravitational interaction over billions or trillions of years, it will either be ejected into the intergalactic void, where it drifts through a darkness so complete that nothing will ever interact with it again, or it will be drawn by gravity into the interior of a black hole, where its matter will be transformed in ways our current physics cannot fully describe, and eventually released back into the universe as Hawking radiation. And if protons do decay, if the standard model's prediction holds over sufficiently long timescales, then every atom in the spacecraft will eventually convert to photons and leptons, spreading outward at the speed of light, diluted into the universal background, indistinguishable from everything else. The physical final place is the universe itself. The spacecraft dissolves back into the medium it has been traveling through. Stardust returning to stardust. The second answer is deeper. The final place Voyager 1 reaches, the place it has actually been heading all along, whether anyone intended this or not, is permanence. Not the permanence of physical survival, because nothing survives forever in the physical sense, but the permanence of having happened, of being woven into the causal fabric of a universe that does not forget, even when it can no longer read, the record of what has occurred within it. September 5th, 1977 exists permanently in the geometry of space-time. The launch happened. The golden record was sealed with human fingerprints still on it. Andromed's dreaming brain was encoded in gold. The pale blue dot photograph was taken. The heliopause was crossed. All of it happened. And in the block universe of relativistic physics, all of it is still happening, always, at its own location in the four dimensions of space-time. The final place Voyager 1 reaches is the permanent record of the universe. It arrives there at launch, and it never leaves. I think that is the most honest and complete answer I can give you, and I think it is, in its own quiet way, one of the most comforting things physics has ever told us, because it means that the things we do with care, the things we build with love and precision and genuine intention, are not erased. Not by time, not by entropy, not by the death of stars or the evaporation of black holes. They are encoded in the structure of reality itself as surely and as permanently as the laws that govern the behavior of matter and energy. Your life is like that too. Every moment of genuine connection, every act of real kindness, every time you looked at the sky and felt something, all of it is encoded in the causal fabric of the universe. The people you have affected, the things you have made, the moments you have shared, all of it ripples forward in ways you will never fully see or know. All of it is part of the permanent record. You do not need to launch a spacecraft to matter at cosmic scale. You just need to live with the same quality of intention that went into building one. Voyager 1 is still out there, right now. As you watch this video, as you breathe, as your heart beats, that little golden machine is crossing another few thousand kilometers of interstellar space. Its signal is traveling toward Earth at the speed of light, carrying data about the hum of the interstellar medium, about the density of plasma in the space between the stars, about the environment in a place no human being has ever been and may never go. And somewhere in Pasadena, California, an engineer is looking at a screen, watching numbers arrive from 23 billion kilometers away, doing the quiet, faithful, extraordinary work of staying in contact with the furthest thing our civilization has ever touched. Hold that image. Really hold it. A human being in a building with coffee cups and computer screens and the ordinary furniture of a working day, connected by an invisible thread of radio waves to a machine drifting through the stars. The thread is thin. It is getting thinner. But it is still there. It is still there. Before we finish, I want to say something directly to you, not to a general audience, to you specifically, whoever you are, wherever you are watching this. The fact that you spent this much time with a story about a spacecraft and the death of stars and the far future of the cosmos tells me something about you. It tells me you are someone who finds meaning in the large view, who is not satisfied with the surface of things, who wants to understand not just what is happening, but what it means that anything is happening at all. That is a rare quality and a precious one. It is in some ways the quality that makes us most fully human, this capacity to look up from the immediate and ask questions that have no practical answer, that serve no survival purpose, that offer no competitive advantage. Questions like, what happens to Voyager 1 in 1,000,000,000 years? What is the universe like after the last star dies? What does it mean that we are here at all? Those questions do not make you more productive. They do not help you meet a deadline or win an argument or get ahead of anyone. They make you more alive, more awake, more connected to the genuine strangeness and beauty of the situation you find yourself in. That is worth protecting. Whatever pulls you away from that quality of attention, whatever makes the universe feel smaller or less interesting or less mysterious than it actually is, resist it. Not always. Not at the expense of the practical and the immediate, but sometimes, regularly, deliberately, look up. Not as a metaphor, actually look up. Go outside tonight, if the sky is clear where you are, and find a dark patch away from the light pollution, and look up. Really look. Give it time. Your eyes need about 20 minutes to fully dark adapt, and most people never wait that long. But if you wait, you will start to see things. The band of the Milky Way, the faint smudge of the Andromeda galaxy, 2.5 million light-years away, the most distant thing you can see with the naked eye. Stars at different distances, different ages, different temperatures, all contributing their photons to the same moment of your perception. And somewhere up there, in the direction of the constellation Ophiuchus, though far too faint to see, far too distant for any human eye or instrument except the largest radio telescopes, there is a spacecraft tumbling silently through the dark, carrying a golden record with the sound of rain and a heartbeat and music from a dozen cultures on a planet called Earth. It is out there right now, and it is ours, built by human hands, fueled by human curiosity, launched by human courage and kept alive for just a little while longer by human dedication. We sent something into the stars, not because we had to, not because it was practical, not because anyone asked us to, because we are the kind of creatures that look at the darkness and want to know what is in it, because we are the kind of creatures that hear silence and want to put music in it, because we are the kind of creatures that reach. We will always reach. It is what we do. It is what we are. And whatever comes next, whatever missions are launched in the decades ahead, whatever discoveries are made by telescopes not yet built or instruments not yet conceived, all of it will carry the DNA of this moment, of this mission, of a small golden record-carrying spacecraft crossing the boundary between the solar system and the stars, keeping faith with the curiosity that built it. That is the final place Voyager 1 reaches, and in reaching it, it takes all of us with it. And if this journey left you with that mix of awe and unease and wanting to know more, then I already know what video you need to watch next. It is sitting right there on your screen. We explore why deep space gets more terrifying the further you go. Trust me, the further out we looked for this video, the stranger it got. That one goes even deeper. Click it. You are not done yet.